Tirupati. Before joining IIT Tirupati in 2017, he served as an assistant professor at IIT Jodhpur, where he was the founding head of the Department of Computer Science and Engineering. Dr. Ramana sir research spans the broad domain of computer networks with a focus on wireless networks, cloud computing, the Internet of Things, and information-centric networking. He has published more than 60 research papers in reputed peer-reviewed journals and conferences. His work on low-cost infrastructure for rural communication won the Best Paper Award at the 14th International Conference on Networks held in Singapore in 2006. To date, Sir has successfully supervised 6 PhD theses, 21 MTech theses, and over 75 BTech projects. He is an active member of the research community, serving as a reviewer and technical program committee member for numerous top-tier journals and conferences. He is a senior member of ACM and IEEE. Dr. Ramana sir also has extensive administrative experience. During his tenure at IIT Jodhpur during 2010 and 17, he held several key positions, including Chairman of Admissions, Chairman of the Industry Immersion Program, Coordinator of the Center of Excellence in Information and Communication Technology, and Associate Dean of Academic Affairs. At IIT Tirupati, Sir served as the founding head of the Department of CSE for 6 years. Since 2020, Sir has been heading the Computer Center, where he oversees the design and development of the Institute IT infrastructure. Additionally, Sir serves as the officiating registrar of IIT Tirupati. Once again, thank you for accepting our invitation and for sharing your expertise with us, sir. We are eager to learn from you and make this session as most enriching opportunity. Without further ado, I request Dr. B. Venkatramana sir to kindly begin the session. Thank you and welcome once again Dr. B. Venkatramana sir and participants. Thank you, sir. Sir, please switch on your mic, sir. Ramana, sir.
Yeah, thank you for the introduction. It's a privilege also for me to address the faculty colleagues, members joining from different places. So today's talk is slightly connected with cybersecurity, more on the networks. I really misread the content because multiple things came in one go. Yesterday I gave for other place on IoT. I thought it's also the same. Somehow it is connected with more on IoT, networking, and little bit on security. So towards the end, you see some aspects of security. So my primary focus is on basically a new networking paradigm, that is information-centric networks. So what I am going to introduce is in the context of IoT networking, what is today and what I'm basically, what we can envisage it right now in future. So let me share my presentation. So I hope you're able to see the presentation.
Yes, sir.
Yeah. So the outline of the talk is the following. So a very brief introduction to IoT and communication paradigms, communication models, patterns, and technologies that we have, and IoT protocol stack. Then a little more in detail, Then move on to something like a new networking paradigm, that is information centric networking. And finally, how the security threats are addressed in IP based networking and the ICN. So, in the context of IoT, like what we see is it is a network of things, where the thing has an ability to sense, communicate, analyze, decide, and act upon. So all these abilities you can see like a particular a component in the Internet of Things world doing. So what we see is a thing could be either a physical object or it could be a virtual object. Here you can see a microcontroller could be a thing, and also a sensor which sense environmental parameters or any other parameters. Uh, so I think we'll be looking at, and even cloud actuators or anything. Is considered as part of this IoT. And basically, the IoT environment you can see as a very constrained environment, where you will be able to see one or more in combination of the following. You can see like the devices in IoT, they may have like a low memory, or they may have like a low power. They may be operating on low power, and they may be having like mostly uh, available bandwidth is also low. Then the link quality will be highly loss prone. So the links are lossy. So you can see multiple of these, uh, the network may be suffering with, or you can see a constrained with. And then you can see the typical characteristics of IoT. There are three components that we see here: the network, then the objects or things, and the services. The what is that we envisage for the network? Network should be able to self-configure, and it should be able to adapt also to the dynamically changing conditions. And network is not a very simple network. It should be able to scale up from simple networking to a large scale network. So in fact, it is, you can see like a complex network. So whatever the solutions one should come up with for networks, they should be able to self-configure, they should be able to adapt to the changes, and they should be able to scale also. Then what it is expected also, the whatever the things we are calling, they should be able to interconnect using the existing protocols. Then coming to the devices or components or things, they can be physical or virtual in nature. Then they some of them may be sensing the parameters, some of them may be processing the parameters, some of them may be executing the actions. So they should be able to reconfigurable. They should be able to programmable. Some of these are typical characteristics for things. Then other thing is like the things should be able to uniquely identifiable. So each one we should be able to uniquely identify, and they should be able to serve with or without or with minimal human intervention. And when you come to like the services offered by IoT, so like right now we may have certain services, but later on the same network may be able to offer many more services. So in order to support the services in future, so the network should be able to have like intelligent interfaces, so that the networks can, that the applications can be built in future. And these services should be readily available from anywhere for at any time and for anyone, so in a in a secured way. So security is one of the prime aspect, and also the availability of the services is also another aspect. Then coming to the communication models that we see typically in IoT. So the first model of communication is device-to-device communication. So for example, you see here in a house, you typically see like a switch or operating like a bulb. So what you can see is a controller may be there, so that may be directly talking to basically a bulb. It is basically called as a device-to-device communication. Devices are directly talking to each other without any intermediate service. So then here typically a device from different manufacturers must be able to communicate. What we envisage here is mostly all the components must be from the same, will be from the same manufacturer, but it is typically expected the devices from different manufacturers should be able to talk to each other. So for that, they should be able to use like a standard communication protocol. So he typically device-to-device communication, they use like a Bluetooth and Zigbee kind of communication protocols or stacks, protocol stacks. So the other one is like a device to gateway communication model. What we see here is you have again a temperature sensor and maybe a device with some other like a sensor that is built in. So what we can see is all these devices are maybe talking to a central device that is inside home, let us say home automation application. There will be multiple sensors of different type will be deployed, and they all will be talking to that centralized home controller, so which we call it as a home gateway. That is what is called a device to gateway communication model. So then a device to cloud communication model where there is no controller sitting at home, for example, in the home automation application. Rather, like they are all directly talking to a virtual server that is available on the cloud, and the end users typically connected to the virtual server and operating the sensors or any other devices connected through their dashboards that are provided by the cloud service provider. So this is basically called a device to cloud communication model. So three models that we see, and typically what is the flow of traffic? So we can say like you can pull the data from the network, right? Or you can push data. Then the network can push the data to the end users. That is called a push type of service model. Then you can pull the network. You can pull the data from the network. That is called a pull type surface. Then you can have a hybrid in nature, like a push and pull. And the third type of communication model that we see here is a publish and subscribe model. What we do is the end users may be subscribed to a particular type of service or data that is they are interested. And whenever there is a new data generated for those services, so they will be published. So first of all, end users will be subscribed, and whenever a new data available, it is basically published to those subscribers. It is published and that is shared with the subscribers. This is a publish subscribe model of communication pattern. And then other thing is communication pattern. So these are all like a slightly like no overlapping terminology, but there is a very clear difference between the terms. So what we see here is a communication pattern. There can be a like no communication between two users. That is, a single user is talking to a single source. So example, a switch transmits a command to a light fixture. That is a one-to-one communication. Then the second thing is like a single user to multiple sources. What you can do is all temperature information from sensors in the house. So what you can see is you may have like multiple temperature sensors deployed inside your house. So you wanted to pull the temperature from all the sensors. So that is called one to many, right? A single user talking to multiple sources, pulling the data from multiple sources, then multiple users to a single source. So that is also like there may be a single source which is basically talking to multiple users. So that's a then many to many. What you see is multiple users talking to multiple sources. So the communication patterns are one to one, or one to many, or many to one, or many to many. So what you said, what we initially we have seen was the vision for IoT. So IoT network should be able to offer variety of services. Then they should be able to adapt, right? The network should be able to adapt, and it should be able to self-configure, so on so. So, and also for foremost important thing is it should scale. The network should scale. So in this context, what you see is there are number of applications that can be built on the top of IoT. So the characteristics of applications also they will vary greatly. For example, some of the applications can be small in nature. For example, the network size, what you can see for some of the applications may be small. And for example, here you can see smart healthcare applications. The network size typically will be a few tens of nodes. And whereas the coverage area for the smart sensor network could be a few tens of meters. But if you look at like on contrary, like a smart transport applications or smart agriculture applications, they typically span across larger distances, maybe a few tens of kilometers. And the network size is also like it's thousands of sensor nodes you may be having. So the network size will vary greatly with from application to application, and whereas the coverage requirements are also they're greatly changing. So what I want to emphasize here is that there is no one measurement, one fit to all kind of situation. Each application will have its own unique requirements in terms of network size, in terms of coverage, and the next slide is in terms of the traffic rate that is generated, and in terms of quality of service that is required for the data that is being transmitted. So each application exhibits a different type of requirements, which should be supported by the IoT. Whatever the technologies that we are going to discuss should be supported. These requirements. Coming into first communication technologies, as just we have seen the network size and the distance that typically expected to cover. So based on these parameters are few other parameters. For example, the speed is another parameter, cost and power, standardization and frequency, whether it is unlicensed frequency band or licensed frequency band. Standardization in the sense whether it is a standardized or it's an open standard or it's a commercial or proprietary. And the power requirements are typically whether they require um, like a low power or high power kind of thing. So then cost, speed is low speeds or high speed. Then distance is any of this, like you can say few meters to few tens of kilometers. So coming on to this, what we see here is when we require our application to support larger distances and require like a higher bandwidth. So what we have to see, what we will see is we have to go for either cellular or satellite kind of communication technology. Then we require ending up with facing high power consumption. So because we need to support larger distances at the same time higher bandwidth, then typically power consumption will be higher. So we should have actually look at into how to meet the power requirements. for those applications. Then you may have some applications, typically they require to serve like shorter distances, but they require higher bandwidth, right? So for these kind of applications, we have like communication technologies. They can be used like Wi-Fi, Bluetooth, or wired interface like Ethernet. And typically, what we see here is like since it is a low range, short distance communication, but still they require like a high power. So, and we also see like a low power consumption. So the applications may not, our sensors may not be required to active all the time. So we can see like Wi-Fi, Bluetooth, and Ethernet, which require like a low power. If you have like a low bandwidth and low power but required to serve for higher distances, then the option for that will be like LoRaWAN, Sigfox, NB-IoT, it's a narrowband IoT, and LTE-M. So these are the four communication technologies that are widely used. In fact, LoRaWAN is widely used as a long distance solution for low power, low rate communication. So typically it serves like a low volumes of data. So any questions so far?
Participants, if we have any queries, please ask Ramna sir, even through voice or chat box.
Yes, sir. So there is one query that I had. So if I say that considering the security aspect, so if I have certain goals of security, will the communication channel change? Like probably considering, say, suppose Bluetooth. I know the fact that Bluetooth may not be so secured as compared to any other communication model. So should one change the model or basically the application somehow in order to meet the security requirements?
Uh, I understood. I understand your question. So whether the solution of this communication technology, choice of the selection of this communication technology uh, is influenced by the requirements of security or not.
Yes, sir. Yes, sir.
So my answer to that is, of course, at the lowest communication layer, you will see like um, the impact of this. But I feel my answer to that will be, I guess, you should have enough security measures at the higher layers. So you may particularly see like environmental factors which are maybe influencing your transmissions, the interference, noise, jamming, like no those things. But of course, communication technologies are so built to basically from the security perspective, but none of these are like you can say Wi-Fi. Wi-Fi has its own security threats. Even Bluetooth has its own security threats.
Right. So you're saying that in case of let's consider the three layers in terms of IoT, which is the perception layer, the lowest one, network, and then the application. So we should improve more application layer security, so that
Application layer security, and
yeah.
as well like network layer also you can build. For example, you have like transport layer security kind of solutions.
Okay.
So yeah, they can be taken.
Okay. Thank you, sir.
Nice question. So
Thank you, sir.
Any other queries still? Okay, sir, I think no queries.
So, yeah, Bluetooth is basically everyone knows about it. We have two variants of Bluetooth. The standard Bluetooth technology is not actually like no, it's a little power hungry. It takes more power compared to Bluetooth low energy BLE. So the standards are available set by the IEEE committee like 802.15.1. So typically, the Bluetooth technology is what you know, like they operate on free license band, that is 2.4 gigahertz ISM band. So they operate a few, probably up to 10 megabits per second data rate, and supports like 100 like meters distances. So the, as you know, like Bluetooth technology is used for device to device communication. It's not like a device to gateway or device to cloud kind of thing. So then Zigbee is coming into picture. This the standards are available in 802.15.4. So why I'm putting the standards here is sometimes people may refer these technologies with their standard number rather than the technology name. Sometimes people may say Zigbee, but Zigbee is a complete protocol stack, and it uses particularly 802.15.4 as its MAC layer protocol. So I think I should correct this. Zigbee refers to the complete protocol stack. It has a network layer, it has an application layers, etc. And its MAC layer has these standards like 802.15.4. So coming to Zigbee, it offers it is used for shorter distance communication, and it offers low speeds, and also it consumes low powers, right? So then it's basically designed for to run on low power devices, typically for machine to machine communication. So you can see like the devices may be directly talking, or they may be talking to a standard sync device, that's a gateway kind of device directly. So multiple, there'll be many different device topologies that we can see for Zigbee-based networks. So they may be one-to-one, or one-to-one in the sense like a device-to-device. They may be talking, or device-to-gateway. They may be communication is happening. So then coming to Wi-Fi, which we widely use, it is for short range, of course. What typically you see is higher bandwidths compared to previous two ones. You can also see another additional thing like a quality of service. For example, if you want to prioritize certain traffic, it is possible with Wi-Fi. And typically the rates, data rates that we see here are something like even a few hundred megabits per second. The latest standards that are coming, like Wi-Fi 6 and all, they support 1 gigabit speed, right? That's These are the standards for the Wi-Fi LANs. 802.11, under 802.11, 11AX is given for Wi-Fi 6, what is known as Wi-Fi 6. Then 11BE, those are the standards given for Wi-Fi 7 technology. Then the communication is typically devices can talk to each other. The devices can also talk to other devices via access points. Particularly for from the context of cellular network, from the context of IoT, Wi-Fi has like a Wi-Fi Halo. It basically supports a long range and moderate speeds and low power. So it operates at sub gigahertz frequency. That's the ISM frequency bands. Yeah, sorry, I'm just looking at some important message. Yeah. We have some interviews in the institute, so I think some member. Yeah. So coming to this long range communication, what are the technologies we use? The first and foremost thing is like LoRaWAN, which is very popular. For example, you have an application to measure soil parameters in your field, and all the parameters have to be reported or collected by a device which is deployed inside your house. So it's probably you may not be having your house in the field. So typically it is a long range communication, long distance communication. So you can use like a LoRaWAN. It operates on unlicensed frequency bands, like no, which are around sub gigahertz, and it operates about like no 15 kilometers distance. You may have like devices separated by 15 kilometers distance, and the it supports like about three um, up to 50 kilobits of speeds, like now you will be able to get with LoRaWAN. Then the typical applications that we can see here are like smart cities applications and smart agriculture and smart environmental monitoring. Then coming to Sigfox, so there is a difference between these technologies. So LoRaWAN is basically open standards, whereas like a Sigfox is basically a proprietary solution. So it again operates at a similar frequency bands, but still it is unlicensed. Then it operates like no to the distances up to 50 kilometers in rural areas. But whereas when you look at the speeds, it operates 100 bits per second. So very low data rates it offers. Then the battery life, you may have like maybe 10 years or 8 years or 9 years. So you may see like devices, the battery power it consumes like a very low battery power. Then typical applications for this communication technology will be asset tracking and utility metering. For example, smart meters deployed by the power grid, they may be taking like a Sigfox kind of solution as a communication choice, and even logistics also. You may see like a Sigfox is one of the because it's the battery support, everything is like no, it's much higher compared to LoRaWAN kind of stuff. Then coming to the other two communication technologies for long distance and low power also, narrowband IoT. So this solution, narrowband IoT, the solution is basically coming from cellular world. So that means like these solutions use the existing cellular infrastructure. That's where like you can see the services offered by these communication technologies are reliable compared to the previous two technologies that I've discussed. So typically it offers like a high coverage in indoor and in urban areas also. And it offers data rates about 250 kilobits per second. And even here, like you can see like a battery lives are typically coming in the order of tens of years. Then yeah, it's again like used for smart metering, healthcare and industry IoT. Then you also see like a LTE-M, which is again uses like a cellular infrastructure. So that's where like you can see like typically very high data rates up to 1 megabit per second. So these are like typically come under the communication technologies like no for low power wide area network. So there are multiple classifications. These technologies come under LPWAN, low power wide area network solution. So any questions? So
Participants, if we have any queries, please.
Sir, good evening, sir.
yeah, good evening.
Sir, good evening, sir.
Yes,
Good
sir.
evening.
Srivasu, sir,
I
carry
have a
on. You are
small
audible.
general doubt, sir. Yeah, I have a small general doubt.
Yeah.
Sir, this communication technology is growing every day. It is good only, sir. But at the same time, due to this signals surrounding of this environment, Is it any health problems will arises that maybe you are focusing or not, sir? Because of even cell also we are continuously like speaking means then there may be heart or some brain. These are all coming now. If you use this technologies, is it any harmful for and also how to suppress those problems? Those way also we are developing technologies are only for communication fast purpose only using. Please clear my doubts, sir. General doubt.
Yeah, typically the radiation that we see from these long distance technology is higher. Even the Wi-Fi, what you see, also has certain radiation effect, but it is in the acceptable range. But whereas if you see like the cellular technologies, we are not directly looking at cellular technologies that requires like more power. Once you charge your mobile, it will drain in a day or something like so that's where like definitely there will be radiation when you look at like a normal cellular communication. But when you look at like from the IoT perspective, they may not be operating continuously. They may be, let us say, take like smart agriculture. So where you will be deploying some sensor in the field, which may be sending every 15 minutes or every half an hour one sample. So that sample is also like a very short packet, maybe 100 bytes or 200 bytes kind of packet. So for these kind of applications, we don't expect any kind of radiation because it's not continuous traffic, and also it is not high. It's just a very low volume, right? We will not have any impact on this. So we will have
Thank you so
definitely an
much, sir.
impact to the cellular technology, normal mobile communication. Okay. So moving on to the networking technologies, what we have seen so far is the lowest level. What are the technologies? What are the options that we have? So starting from a personal area network to LAN, then wide area network solutions, then low power wide area network solutions. So the solutions can be categorized into multiple baskets. Then coming up to different layers, I'm not getting into in these layers in detail. What we see at the top are the application layer protocols, which are widely used in IoT networks. So constraint application layer protocol scope is widely used, and it directly operates on UDP, like UDP as a transport layer protocol. And if require security for the communication, they may use like a DTLS, like transport layer security. Like, no, this is an add-on. Something similar to that, you can see MQTT is another protocol that typically offers services like publish, subscribe kind of services to the users or to the applications. And you can add on further, you can have security by transport layer, TLS kind of layer that you can adopt in the middle. Then you have like MQTT and HTTP, all these things directly operate on a transport layer protocol called TCP. So why I'm emphasizing here is like these are the optional ones, TLS or DTLS, whereas they require any one of these two transport layer protocols like UDP or TCP. But lower, further down if we come, so we see like for the network layer, we see like Internet Protocol version 6, IPv6 as an option. Like we use extensively today IP version 4, IPv4. So that is in the wired networks, we use like IPv4. But when it comes to IoT networks, as I described earlier, the network size may vary from few tens of devices to few thousands of devices. So in order to have a scalable solution, instead of IPv4, IPv6 is selected as a preferred network layer protocol for IoT networks. So IPv6 cannot be directly run on these MAC layers, whatever we see here, like 802.15.4 or BLE or Wi-Fi, any of these things. So there is a kind of like a adaptation layer that is called a 6-low PAN. Or 6-low. Anyway, you can call it as 6-low PAN or 6-low. So this is an adaptation layer that is to adapt IPv6, which is typically designed for wired network, to the protocols that are designed for low power, low data rate, like no situations like 802.15.4 or BLE. So I'm going to emphasize on IPv6 and 6-low PAN. So rest are all like they have their own role playing, but IPv6 and 6-low PAN, they have greater role like no they're playing for in the IoT networks. So what you see is typically communication here is you have an IoT network here. So devices may be talking among themselves within the network, or a device may be talking to another device which is not in the same network but outside, or a device may be talking to even not even like no in the near vicinity, something which is connected to the internet, a device on the internet it may be talking to. So typically, you will be able to see any of these things happening in typical IoT scenario. So I said like IPv6 is taken as a preferred network layer solution for IoT. IPv6 was designed back in 1990, but it was commercially deployed. The first deployment you could see in sometime in 2007. The main reason for bringing up IPv6 is to address the shortage of address space of IPv4. So we ran out of internet IP addresses long time back, but still we are surviving because of few other solutions, hodgepodge solutions. But IPv6 is coming up with a very clean solution to support a very large address space, using which it will take like it may take like no we may not run out of the addresses in near future. So that is basically um, like with IPv6, which has a very large address space, support for large address space. Then what we see with IPv6 is typical packet size that we see with IPv6 is nearly 1300 bytes. That's what is IPv6 packet size. Whereas IPv6 is operating, if you look at the figure here, IPv6 is operating on MAC layer protocols which have very short frame sizes. You can see here MAC layers typically take like 120 bytes, but IPv6 typically it is expected to carry 1300 bytes. How do you translate? How do you transmit these 1300 bytes packets on a MAC layer frames of 127 bytes? That is what is the question. So there is a mismatch, right? You have larger packets and to be carried in very short frames. So of course, like we have to go for fragmentation, right? So that's what typically like no fragmentation is an option to divide a larger packet into smaller and send it. But 127 bytes is too small. How do you utilize this 127 in the normal case. That's what we see in the next slide. So, for example, if you see typically a packets, what we see here is like some number of bytes required for MAC layer header, some number of bytes required for IPv6 header, some number of bytes required for IPv6 payload. IPv6 payload also contains the transport layer header and the transport layer payload, etc., etc. Right. So let us see like how whatever we see is a maximum frame size as 127 bytes, out of which you can say like the frame. We said like frame requires like some number of bytes, right, to send the information. That is about 25 bytes. 25 bytes are required for sending MAC layer information. Then that leaves us with 102 bytes. Then if you want to add on some security at the link layer, you require like a 21 bytes of header. That leaves us 81 bytes. Then you can say like IPv6 as it is, it requires like a 40 bytes for its header. Then UDP, if you take it, it requires like another 8 bytes. So totally when you count all these headers, like now we'll be left out with about 33 bytes for the payload, which is negligible or which is too small compared to the header, the number of bytes we have meant for the headers. So we have kept like a 75% of like no entire packet is carried with control information, whereas only 25% is used for sending actual data. So that is really not acceptable. So what IP, the adaptation layer in the middle, what I said, like a 6th low pan, it basically goes through a process of compression, header compression. So by reducing whatever you see here in the headers, let us say IPv6 header and UDP header, together 48 bytes required in the normal case, that can be compressed to 6 bytes, right? So then that leaves like a 75 bytes for the payload. So that's a great reduction in basically the control overhead we can see. So what I want to say is IPv6 is sitting in between the network layer of IoT and the MAC layer of IoT in between. So this is basically to bridge the gap between the packet sizes. And not only that, it also like goes through a smart header compression mechanism to reduce the control overhead and permit more of payload, right? That's what is basically one of. You can see here what is this 6LoWPAN, the responsibilities of 6LoWPAN. It is basically it is responsible for encapsulating of the packet, right? In the MAC layer, larger packet into smaller frames. How is it doing? It is, if required, it can fragment the packets, and on the receiving side, it can reassemble those packets or fragments. Then it has a mechanism for compressing the header so that it can send more information, more from the payload. Then it is link level, link layer packet forwarding is also possible. I'll discuss that in a minute. And it also has like auto configuration and neighbor discovery. So one of the requirement that we mentioned earlier was the networks should be able to auto configure, right? So they should self configure and adapt. These are the two features. So it is basically coming under self configuration feature that we envisage for IoT. Then the neighbor discovery is another feature that we can see with the 6LoWPAN. So 6LoWPAN, you can see here, this is little more technical, right? So what we see, the figure on the top, it is basically a layer 3 forwarding, right? And the figure on the bottom is the layer 2 forwarding. So what happens is when typically a source is sending packets to the destination, they will anyway go through all the layers at the sender, and at the intermediate nodes they'll go all the way to the network layer. That's where, based on the network layer address, routing decisions are taken accordingly the packets are forwarded. So if this is the case, we call it as layer 3 forwarding and also route over forwarding. But if you really look at whatever, like you see number of devices in between the gateway and the sender. Let us say destination is the gateway and the sender is some node in the network, which are separated by multiple IoT devices in the middle, right? So you need not to take the packets or take take the fragments to the network layer. Rather, from the link layer itself, you can make like forwarding decisions and send it to the gateway or the actual destination. When you do this, this is called link level or link layer forwarding or mesh under forwarding. Either of these two things are. So for example, in your college network, to reach a router, your packets may go through multiple switches, right? Switches are basically layer 2 devices. That is in the wired network context. But in the wireless networking concept, you may have several nodes in the middle. They may not be actual communication switches. They may be typically any other receiving or sending node. So they will take the packet, receive the packet, and make a decision at the layer 2 itself and forward it. This is typically to bring whatever we see in the wired network in the wireless, into the wireless. So then I said, like, what is the purpose of auto configuration? When your node basically want to join in an IoT, what it requires is it requires to know, it requires to get a uniquely identifiable address. That's the first thing, right? Every object that is connected to the IoT should have like a uniquely identifiable address. So how do they generate this? So one of the this is a process. Auto configuration is the process through which the nodes can generate uniquely identifiable address, right? Without an entity like DHCP. In the typical wired network, we'll have a DHCP, which when you connect it when you start your device, it automatically gets like an IP address from DHCP server. And here it is, you cannot expect a DHCP kind of server, existence of DHCP kind of server in your network. So what happens here is when a node comes up, it will prepare a part of an address locally by itself. So that is called a local ID. You can say IID, interface ID, we can call it as. It is prepared locally by the node, right? That whatever it has prepared locally by that node, it will share with its neighboring devices, right? Then if the neighboring devices have not reported anything about duplication of this address, then it will ask for the network prefix. So when you look at address, a part of the address is prepared locally by the node. Another part is called like a network prefix, which it should receive from the network. So once it is sure, like no other one has generated a local ID or interface ID, so then it will ask for the network prefix. So by sending this RS packet, RS is a message type. So typically, So it is called as a router solicitation message. So using this RS message, a node will ask for network prefix, and in return, the router sends network prefix through a message called RA message. That is router advertisement. 1 minute, please hold. Sorry, this is from office. So what I want to say here is like no auto configuration, using which a node should be able to prepare its own IP address. So partly it prepares first locally and advertises to all neighbors. If neighbors do not say like these neighbors declare that this is a unique address, then it will request the router to share the network prefix. Once it receives the network prefix, so it will put like network prefix and local interface ID together and take it as like no IPv6. So this is a way without having any entity like a DHCP server. A node will be is able to automatically prepare its own IPv6 address and start communicating with other devices using that address. So that is basically coming under auto configuration. Then the typical routing, how it happens in IoT networks, right? So one I said like IPv6 is a protocol using which it basically offers an addressing scheme to address to provide 2 to the power of 128 addresses. Then, but when the packets are coming with these addresses, you should be able to route these packets. So for that, you should be able to have like a routing protocol. So typically, the routing protocols used in IoT networks, you can see here, RPL. RPL is a routing protocol for IoT networks. So whatever the routing protocols that we see on the internet, typically, can you recall the routing protocols used for the internet, like OSPF or RIP or BGP? They all will have like a lot of information exchange happening, right? So one cannot think about the typically uh, like a OSPF kind of protocol, because any small change in the network will result in sending lot of messages to re-establish the routes and other things. So that's where like the standard routing protocols used on the wired networks will not work here. So that's where like IPv6 has come into existence. It is basically to offer the routing services over low power lossy networks. So one of the beauty of this RPL is you will be able to use different routing metrics. For example, you can establish or find out a path based on the shortest latency, or you can establish a route between two nodes by considering the energy conservation, like how much energy you save. Then you can also see like link reliability. So for example, if you want to send a single message, what are the typical number of transmissions that are required? So ETX is basically expected number of transmissions. So for every message to send, if you take just one transmission, that is highly reliable. For example, if you want to send like one message you require like 2 transmissions. So of course, like each transmission, like one is a primary transmission, and you are making a second transmission because the other transmission was lost. So expected number of transmissions is another metric can be used for reliability. Then finally, hop count can also be used as a metric, right? So the RPL it supports any kind of these routing metrics to be used to establish the routes. So the basic like now when you consider the whole thing as a graph, so what typically happens is RPL protocol offers some kind of like a many to one kind of communication model, right? What we see here is like on the left you see like a direct acyclic graph where there are no cycles in the graph. You can see like the nodes that are colored in green are basically receivers. So for example, this is like what kind of thing you can say it as many to many kind of communication. But whereas here RPL supports like a many to one kind of communication model. So here the receiver will be the root of the particular graph, you can say. Then all the transmissions are heading towards that particular node that is acting as a root in this. So this particular thing is called a DODAG, destination oriented direct acyclic graph. So RPL basically tries to form like a destination oriented direct acyclic graph where you see like a node which is receiving all the transmissions at the root, right? So that's where like you can see like how like the routing metric you can see in terms of like how close you are to that particular destination. If you are like one hop away, you can say like your rank is 1. If you are like 2 hops away, you can call it as a rank 2. Like the distance, whether it is a hop count or whether it is a energy, whatever we consider, how close you are to the root, that defines like no the rank is defined based on the closeness proximity to the root. So this is basically explaining what is that rank. Rank is basically here when you consider hop count as a metric, like you can see like this is the one that is root, acting as a root, and it is at rank 0. And whereas all the nodes that are one hop away, they are basically called as like at rank 1, and 2 hops away at rank 2, and 3 hops away at rank 3, so on. So like the distance is measured or whatever metrics we consider. We just give a rank, and we just take like apply finding the like no while making the decisions we'll take the rank into consideration. So this is an example scenario you can see here. So the figure on the top, there are 3 IoT devices. So like the 2 on the extreme sides, you can see they are directly connected to the root. That is what is a gateway, we can call it as. The third node, which is standing in isolation, it cannot directly reach it. So it can reach either this or this. So that's where like you can think of like what is the total cost of the path from a particular node to the DODAG. That's the root of the DODAG. So when you consider like expected number of transmissions as a routing metric, what happens is this is what is a scenario you can get it. So this particular device, it can send this node with the expected number of transmissions 1. So every transmission reaches here. So there is no loss. That's why expected number of transmissions to send a message is 1. Whereas here expected number of transmissions is 1.5. For example, every 2 messages you send, you need to make extra effort to send one more. Like 3 messages, ideally you will be spending, right? So that's 1:1.5, right? Every message requires additionally some rate transmission, right, with some high probability. So if you want to send directly, this node can also reach it, but expected number of transmissions are three. You will just send a packet, it may get lost. You send second time, it may get lost. You may send third time, it may be transmitted. So that's where it is coming as expected number of transmissions is three. So when it is something like ranks are established like this, the cost, you can see the path is something like what is the shortest. So 1.511, this is basically the cost of the path is 2.5, and here it is 2, here it is 3 directly. So here it is expected number of transmissions are taken into taken as a metric to establish the paths. So that is typically a scenario. And also you can have like a multiple metrics in combination you can use and establish the routes. For example, you can see there is a node here circled, and it has to the shortest distance to that to reach the gateway here is a path, direct path, right, via these nodes. But as and let us say this is basically draining off much faster. So what it can it can take it into is like energy conservation, also take it into account while minimizing the expected number of transmissions. So it may set up both the things into account and then set up an alternative path by excluding whatever the node you see like that is going to die. So all these things are possible with RPL. Right. But the limitation of the RPL is, as I mentioned initially, you may have like a point to point. A device may require to send to another device in the same network, or point to multi-point. A device may require to send to multiple devices at the same time. That's you can say multicast, then multi-point to point. So typically, the kind of support that is offered by RPL is multi-point to point. So here every node which are like acting as either intermediate nodes or leaf nodes, they will be able to send to the root of the node. That's called multi-point to point. But whereas if you want to see like a point to point or point to multi-point, they are not coming in a very clean as a clean solution. Rather, they all have to send it to the like let us say this node D wanted to send something to all. What it can do is it can send it to the gateway. Gateway can further send it to a node that is the actual destination. So they are kind of like tweakings. It's not a very clean solution that is provided. So to address these challenges, so there are like few extensions for RPL. One is like a point-to-point RPL. This is for the point-to-point communication. Then MPL is for point-to-multi-point communication. So a variants of few variants of RPL we can see in the form of like a P2P, RPL, or MPL. So that actually completes what is happening today. Today is basically largely driven by IPv6 based IoT deployments. But what happens, what are the drawbacks I can discuss? Any questions so far?
Participants, if we have any queries, please. You can ask Ramana sir if we have any queries, participants. Sir, we got a one query from chat box, sir. What does the number represent in the tree air, sir?
Yeah, sir. Actually, it is given one from root to left IoT and right IoT. You have shown one tree structure, where we have found left and right, and then middle. Middle is not connected to the root, directly connected to the root. So it will take the left side IoT or right side IoT house side. Sir, just I want to know the number you have given the numbers 1, 1.5. Just I want to know what are the numbers. That is whether it represents cost or what is the weight actually.
Yeah, these are link weights. The link weights here are like no derived from the expected number of transmissions.
Oh, okay, okay. Number of transmission, you guess. Then what does it, sir? 1.5 it is mentioned, sir. I couldn't understand. 1.5
Correct.
means?
Let us say you make 100 packets. So you to send 100 packets, you have to send like no, you have to make like no, you have to send 150.
Oh, okay, sir. Okay,
That
sir.
is like it. See what you see like with some probability we will lose the packet, so you have to retransmit. So that retransmissions when you see like for every 100 packets you may have like a 50 retransmissions. Putting together 150 you will be making.
Okay, okay, sir. Thank you,
So for
thank you.
example, here you can see the link cost is given as 3. That is the 3 transmissions for every to make like one single successful transmissions. So
Yes,
let
sir.
us say you will send 100 packets, right? Right, 100 transmissions you expected to make, but it is making like a 300 transmissions. Remaining 200 are to read. Those are the retransmissions.
Okay, sir. Okay, sir. Thank you, thank you.
So that's basically taken as like no. These are all different metrics that can be used by the RPL protocol to establish the routes. So as I
Okay,
mentioned,
thank you.
this is yeah, thank you. This is basically for multi-point to point communication. However, you will see like variants of this are there for point to point communication and point to multi-point as well. So coming to what is this information centric networking, right? What we see IPv6 based network or IPv4 based network, that today's internet or IoT network, the solutions are pretty old. Like for example, IPv4 that came about 1960s or 1970s. It's almost like a 40 to 50 years that is in existence. What we see is still we are able to use those solutions which were like no, which came into existence about 40 years back. At that time, the idea was like let us say mostly to connect a device and perform some computation or share a message. The kind of needs those days were different from the kind of needs that we see today. So today, what we wanted, let us say we wanted to watch a cricket match or PKL, Pro Kabaddi, or anything, right? So what typically we need is we don't want from where the content is coming. We just need like know how fast we can get the content, right? We need this content. How we get the content is it's not a point, not a prime concern today. So the operations, what we see then and what we see now, there is a drastic shift. So earlier, how to get the content. Now, how fast are like no, the content is basically I need this content kind of thing. So content is a prime now, and whereas the host is like no, back in like. 20 years 30 years back like host centric, so host was looked at the center, but now it's the content is looked at the center. So so if I want to put it precisely, the information centric networks, the information is the key, right? So how you get the information is not the matter, like so that's what is basically I want to put on. The same example, if you want to watch a movie, so you want to you movie watching movie is a prime concern, but how to get that movie content is not a matter, like so so information or data or the content is the key in the information centric networks. So so far what we see is everything is coupled with either a device or it is coupled with some location, right? Information, but now what we see in the information centric networks is the location of the information and information both are basically decoupled, right? Information is decoupled from the source, and now it is independent of its location, right? That is what is a very precise term if you can understand. And so So since the location of the information and the information source both are basically made decoupled, uh, so you do not require to worry from where this information is coming. You can simply watch if the information is coming from coming in a secured way. What you have to ensure is whether the information what you received is authentic information. That authenticity is very important. But where it is coming from, whether it is coming from your the node which is next to you, or node actual producer, or somewhere in the intermediate node in the network. So all these things are not that important to you, whether you have received an authentic information or not. That is what is the one thing. So here information is identified by its name, but not by its location or by its provider. What we see so far is information, let us say www.iitmadras.com or iitmadras.ac.in, iitm.ac.in. So what you expect is the information, everything is maintained by the IIT Madras, and the information whatever the request whatever you send, it has to go all the way to the IITM server, right? What you internally get is an IP address of an IITM server from where this information can be pulled, right? So you are in the whole process is going on identifying the host or the machine that is hosting this information, right? I think that is a precise point. So you wanted something, but what we are doing is you are spending some time on resolving like how to get that information, how to reach the machine that is hosting that, right? Then the information is coming. So your primary concern is how to reach that machine rather than what you are getting. So I'll just go a few more details, like now you'll be able to get a clear understanding of this. So in information-centric networks, what we see is another feature of ICN is the network manages the information, not the end host, right? So what we see is right now, when you are talking to a particular machine, only that end machine is sending to you that information, but there's no knowledge of that information to the network, right? But ICN network can also manage the information, and network also can give you the information. So network will have some caching capabilities, right? That's what I want to say. Like network must be aware of what is the availability of the content. That's what is you can see in the ICN. So this idea came in sometime back in 2007 by Van Jacobson. So this idea basically translated the information-centric network. The idea basically translated into a practical networking solution that is called NDN. NDN basically is an implementation of an idea of ICN, right? You can see this for particular figure. What you see is there is an information producer here. Then there are two consumers from the same network. They just wanted that information. What happens is the consumer will send a request, and it is returned back. And consumer 2 also will send the request, and it is written back as separate, this thing. So now network is not having any idea of whether these two are different or whether they are same, or whether for both of them it has gone all the way to the actual producer and returned that request, right? But you see the other case here. In case of ICN, what happens is network has caching capability. In the first, when the consumer 3 sends a request, it will cache this request or the response to the request at multiple places. And whenever a request for the same comes in, right, from different users, it will basically taken out from the cache and it will return to the end user. Do you see any difference? One is like end to end happening. The other thing is in ICN, it need not to be end to end, because network will be able to cache the data. And if something is available in the cache, the network can return from the cache to other users. Are you seeing anything similar, or have you seen something? You must have seen something like a proxy server.
Yeah, sir. Duplicates may be entered, sir.
Yeah, actually, you must have had a proxy server when many users from the same network contact the same server. Then what happens is only the first request, when the first request goes and complete thing is fetched and cached in the proxy server, and the same content is returned to the other request. So this is a kind of cache proxy server, but where it is a proxy server is basically limited to an enterprise, right? It is not actually provided by the network. But here in ICN, the network by default, the nodes will have like a caching capabilities. They can by default cache it, and they can return from the cache, local caches. So that is what is a difference you can see. Even if you look at today, content distribution networks are there. So instead of sending the request all the way to the original server, the request can go to the nearest content distribution server, and it can be returned from the same. There is some kind of overlapping, but by the principle of the designing principle of ICN, the network will cache. So which is missing in today's IP networks. So then question comes comes out whether we can replace the entire internet with IP-based networking with ICN-based solution. It is impossible to replace. But what the internet I'm talking about. But what we can see is in the IoT domain, instead of IP-based IoT networking, we can see ICN-based IoT networking because of these reasons that are listed out. Whatever we discussed, IPv6, R6LoWPAN, they're all customized, right? They're basically meant for internet, wired internet, but they made it some kind of fixings have been done to make it suitable for the IoT. Even then, some protocols like a TCP and all, they are too heavy for IoT networks. And even some of these things are really not possible. So I said like RPL can do point to like a multi-point to point kind of communication. So the current IP-based networking has severe limitations to meet the growing needs of the IoT networks, right? So what I can suggest, probably 7:30 is the time that is given, so I can take like another 5-10 minutes to quickly wrap up, right? So I just want to highlight the features of NDN, right? So in NDN, so what you see is whatever the content you see, the content has a name, and you just say the network like, no, I want this content. You just give the name of the content that you want it, right? So the network, either it'll get it from any one of the node on the network, or it may all the way send that request to the actual producer of the content. So it's the network responsibility of the network, whether it is getting it from the local caching, some nodes in the network or actual producer. That's as I said. So then if you can recall, when you are moving from one network to another network, so you will not be able to contact your local network, right? So let us say you are going on, you are visiting some other organization, and you wanted to contact a machine in your network, which is not possible because the same address you cannot use it, right? Because they are tied up with your organizational IP address. Whereas here, the address is not an issue. So what you see is you want the content. So the solution here is like a very simplified mobility management that we see with NDN. And there is something like a very native support for the multicast communications and multi-homing communication, right? So multicast is anyway, as I said earlier, like internet has no a clean solution for making multicast, right? And multi-homing is if you have multiple interfaces for your device, you cannot receive the traffic from all the device, all the interfaces, the same traffic. For example, you are downloading a movie file, right? So you cannot enable both the interfaces of your device and then receive from both the interfaces, because that is not possible with the current IP based networking. Whereas in NDN, you will be able to do multicast communications much easier, and also multi-homing, like all the interfaces, you can receive the content from all the interfaces, whatever are active currently. And you can also load balance, like by distributing the load across all the interfaces that are available, you'll be able to load balance as well. And and another important thing I want to highlight here is like the security in ICN is much better compared to the IP based, because by principle, what we are by the design principle of ICN, we worry only the content, whether the content, whatever the content that is produced by the actual producer has been received or not. That is the only concern for an end user. Rather, how this content has come to us, right? It might have come from a node which is sitting next to you, or it may be coming from the actual producer. That is not a concern. Whether you have content, whether you have received a content, right content, right? So, right, how do you define a right content? So, producer must have produced some content. So, the same content without any modifications, whether you have received or not. That's what is like. Now, authenticity of the content is very important. So that's what is a prime concern. So when the sender basically produces the content, so that will be encrypted, or that will be signed by the content, by the content producer. Then you will verify only whether it is properly signed or not. If it is signed is verified properly, then what you do is like you can take it as like no, the content is authentic. You can make use of it. But whereas what happening in the IP networks is, so you are worrying about like the endpoints. So securing the endpoints you are seeing like, but you are not worried about whether it is you are receiving the same content which is produced by the actual producer. I hope you got my point. On the internet, that's what is not our worry. We are securing both the endpoints, but not the content. Whereas in ICN, we wanted to secure the content, not the endpoints. So I just skip some of this because I prepared a lot more. So as I want to, I'm basically advocating for the ICN, information-centric networking, or NDN. NDN, as I said, it's basically an implementation, a realization of the idea of ICN is basically NDN. So as I said, like names have been used instead of the addresses, and you basically give a name and ask for a name, and the network will fetch you the content. All right. So there, of course, for any kind of network, when the node in the network receives that name, then it should be able to forward it to the other nodes in the network, and finally that name will reach the actual producer or a node having that content in its cache. Either way is fine, and that's where the content is returned back to the requester. So this is how forwarding the names. Then how do you manage the content at different nodes in the network? Like, what are the caching principles, right? Then how do we basically, when the caches are full, so of course we have to go for cache replacement. How do you go, what kind of cache replacement policies that are there? So these are all the topics, research topics that are people are working on. One thing is what kind of naming scheme mechanism one should have, and how do we forward these requests containing the names of the content, right? And then that's forwarding or routing of the request. Then the third thing is the caching related issues, like how do we cache the content, how do you replace the content. Then the other thing is like how do we offer services, better services, quality of services. So these are all design different research aspects that are there related to ICN. So here what we see is for the memory footprint, how much memory is consumed by IP-based networking, IP-based networking software and ICN-based networking software, right? So you can see ICN-based is basically NDN, right? And IP-based, what I discussed, COAP is an application layer protocol. It uses like a RPL for routing the packets, and it works on 6LoWPAN. So this is IP-based, right? So typically you see multiple implementations you can see for IP-based versus ICN-based. So where is it taking more memory? Obviously, like IP-based solution is taking much higher memory. Of course, like 3 to 4 times higher memory compared to the ICN-based. So as I said initially, IoT, the devices in the IoT or the nodes in the IoT network are constrained by power, by memory, by bandwidth, and other things, right? So you can see which one is taking more memory, or you can see IP-based. So obviously, ICN-based solutions one can think of they are not as resource hungry compared to the IP-based. So what we see here is some of the security threats that we see commonly today. One is denial of service. So what you see is it is a very known kind of security attack. So how it has been addressed in IP-based and ICN-based networks, right? That's what is an interesting thing to look at. So something like you wanted to make sure somebody some server which is you want to make it busy and reject all the legitimate requests. So that's basically you're making somebody purposefully busy so that it cannot process any more legitimate requests. That's what is basically denial of service. So a distributed denial of service is something like instead of one person doing that attack, multiple people, they do the similar attack so that that resource will be busy and throw out all the legitimate requests. So that's a denial of service. And impersonation and spoofing, it's pretending an attacker will pretend like he or she is an honest or some other person and make a request or respond to a request. So that's an impersonation. Then man in the middle, it's basically there'll be two nodes communicating. There may be somebody sitting in the middle, right? They may be intercepting all the messages and maybe changing the what is that request responses, and probably they may be later on replaying those genuine requests, genuine responses to other requests that are going to the same server. So all these things are possible in man in the middle kind of attacks. Of course, like a Sybil attack or denial of information attack, they are very much similar. Sybil attack is similar to like rather than one person, then multiple people doing it. For example, let me go through one by one and then see. So in denial of service, so what happens is when you have only one server is offering the service, of course you can make that server busy and then crash that server. So subsequent requests from the legitimate users all get denied. That's what is today's scenario with IP, right? But whereas in Indian, what we see is your request or your content is not only available at the producer, it is also available in the network. Every node in the network or several nodes in the network. So what you can do in Indian is if the producer is busy, there may be some other node that is available to serve your request. In a way, you are bringing down the effect of denial of service, right, in Indian. Of course, have you understood this point? In IP networks, the information is maintained only at one server, right? So if you can crash that server, that's all, like entire service disruption can happen. But whereas in Indian, the information is maintained by principle I'm talking about, by the design principle of Indian. The information may be available at multiple points. So it is difficult to attack all those points, right? All those locations or all those nodes. So that's where like the impact of denial of service or distributed denial of service is much less in Indian. Similarly, impersonation and spoofing, so which is possible in IP networks, but here what you are because in here you for sure in Indian, if you receive a content and which is signed by the producer, and if you check the sign and then you can get re-verified like no sign matches, then you can say like your content is on that authentic. That is what is possible in case of Indian. And to get that effect in case of IP networks, you should go for a very complex and solutions kind of IPsec etc, which is not by default you get the security inbuilt in IP. Rather, you should go with some complex solutions like IPsec. And Indian by design principle, every content will be signed by the producer. So if you are able to validate the sign or verify the sign successfully, you for sure take that no, that is the right content, authentic content. That is possible. Similarly, man in the middle attacks, that is they're possible in IP networks. To protect from the man in the middle attacks, you should actually use like these complex solutions like a TLS or IPsec kind of solutions to protect from man in the middle attacks. Whereas Indian, that is not there. Only like content if it is signed and if it is verified successfully, you can say like the content is not tampered and you have got the right content. And the reply attacks, Sybil attacks, and denial of service, they are very much similar. So the advantage that is coming for NDN is from its design principle of protecting the content rather than protecting the endpoint. So that's what has been mentioned here. A stronger protection against the attacks due to cryptographic data-centric security. Here data is prime, so that's what you are protecting the data. So not the link or nothing else. So, and you have like in-network caching that will reduce the failure of one or other nodes will not affect the actual communication, right? So, and it decouples the trust from the endpoints. Rather, it basically keeps like the producer itself. If the content is properly signed and verified, you can take it like we got right material. So security is coming from its design principle. rather than any other ad hoc solution that is actually available in the current that came into the current internet, right? So all these are ad hoc solutions, like whatever you see, IPsec or TLS, transport layer security solutions, or DTLS, or any other security solutions that you see. They're all ad hoc. Ad hoc in the sense they came later, much later compared to like no the inception. But you see, like security by default came into the design principle of ICN, information centric network. So like how do you, let us say you have got like a two solutions. One is like IP based networking, other one is NDN based or ICN based networking. So if you want to look for mitigation of like no protecting from any of the attacks, the preferred solution is only NDN, right? If you want to get like, whereas if you want to solution, if you want like no, if from the cost perspective or from the adoption perspective, if you look for, so ICN IP based networking, because you see IP is obviously 50 years old solution, all right? Of course, some of the add-ons, all those things came later on, but the by it's about 50 years old solution. So obviously there will be many players in the market. Their cost will be less compared to ICN based, but ICN is basically by design principle. It has security inbuilt, so it's and it's what is that I want to say is it's a preferred solution for future IoT networks. So I guess with that I conclude today. What we see is IoT is basically to be considered as a global infrastructure, and it has to offer, or it is expected to offer intelligent services to anyone, anytime, anywhere, without any distance, geography, or any of those restrictions. And obviously like no, so it's variety of requirements, like wide range of requirements in terms of the speed requirement, or in terms of any other. So there should no single solution, right? There are multiple solutions that are available, so depending on the requirement one has to choose. Then IPv6 based IP networking is seen as today's solution. But whereas an NDN based or ICN based solution that is basically seen as a promising technology or networking technology for tomorrow's IoT networks, right? So, and one point I wanted to emphasize here is the security is coming into the solution from the design itself. So rather than add-on, right? So like it came into IP. So with that, I just close my presentation, stop my presentation. So if any questions are there, I shall take.
Participants, if you have any queries, you can ask Venkatramana sir by voice or by chat.
Sir, your presentation is highly insightful, sir. Very useful to me, sir. Thank you so much.
Yeah, thank you, madam.
Any others, sir? Any other participants?
Sir, good evening, sir.
Good evening.
Sir, actually, whatever the possibility, whatever the implementations we have in NDN, can we apply the same for IP networking also from external sources or from external implementation?
Can you repeat?
Sir, actually, as of you said that NDN networking is better than IP networking, right, sir? In terms of several considerations.
Correct.
Sir, can we apply any external mechanisms to the IP network to become as a NDN?
For example, I can tell you. So if you want to set up an NDN network, what you can do is like you can take simple Raspberry Pi devices or any of this like now single board computers, So, how you install like IP based or whatever IP based is coming by default with your OS software, but NDN is coming on the top of like these things as a separate software. Like now you can install and do it. Does it answer?
Yes, sir. Then in that case, both are. That means we can implement both in the same. That means both are same, right, sir? When we apply the from external mechanism.
No, no, not both are same. So what I want to say is like you need no need to have like your IP network protocol stack at all. Rather, whatever NDN once you have implemented and all the devices, whatever you see, like they are communicating with each other on the principles of NDN.
So that's okay, sir. And then one more question, sir.
Hmm.
Sir, is there any hybrid implementation of NDN and IP at any field?
Of course, like what we expect is NDN based solutions are at least at some point they should be integrated with internet, right? So what I see is an NDN based machine talking to an IP machine, IP based machine. So that is possible.
So that means in what areas we can implement, sir, in a hybrid mode?
No, hybrid in the sense like a node having these both protocol stacks. That's what you mean, is it?
Yes, sir. Yes, sir.
Um, s- a node on one side it can part of an ICN network. On the other side it can be part of IP network. That is still possible because it's basically a protocol translator, right? One form to another form it is translating. In a way, if I want to say something, see, let us say within IP networking itself, some devices may use IPv6, other devices may use IPv4 only, right? Some
Yes.
devices use only IPv4, some other devices only use IPv6. How do we have communication between these two? There can be one node sitting in the middle, which is
Yes.
receiving all this traffic from either wall. Like no, it is translating IPv6 to IPv4, IPv4 to IPv6. That's the protocol conversion is happening. But these protocols are in the same stack. But
Yes.
if you look at like ICN is one protocol stack, and the other one is like ICN and IP is a different protocol stack. So the protocol conversions the same way what I explained earlier may have, right?
Yes, sir.
ICN traffic can go to IP network and IP traffic can go to the ICN network.
Okay, sir. Thank you,
But
sir.
some translations have to happen in the middle.
Yes, sir. Transitions.
This is called integration of IP and ICN networks.
Yes, sir. Yes, sir.
Shashikala ma'am,
Madam.
shall I come, ma'am?
Yes, ma'am. Yes.
Okay. Thank you, sir. Good evening to once again. On behalf of SRIT management, organizing team, and participants, it is my privilege and honor to express heartfelt gratitude to Dr. B. Venkatramana sir for sharing valuable insights and in-depth knowledge with us today. Your, sir, your presentation on Internet of Things, IoT communication, models and technologies, different types of networks, IoT protocol stack, IPv4 and IPv6 addressing, and especially NDN services, and many more advanced topics was truly enlightening us, sir. We hope this is just a beginning for a long lasting relationship with you, sir. Your insights have been invaluable, and we look forward to future opportunities to learn from you, sir. Once again, thank you so much for your excellent session and real world examples, and especially patient response for our participant queries have left a lasting impact on all of us, sir. So, once again, thank you, sir. Please, Nagatamna, sir, we will, with your
Yeah.
permission, we will take a group photo, sir.
Yeah, please. Thank you very much. I do like even after office hours, I see great participation and enthusiasm also in terms of asking questions. Which I miss at many places.
Participants, please switch on your videos. Thank you, sir.
Sir, thank you very much, sir. Venkatramana, sir.
Thanks.
Thank you, sir. Thank you very much, sir.
Thanks. So I'm signing off. Thank you very much. Yeah.
Thank you,
Yeah,
sir.
okay. Thank you, sir.
Vishakala ma'am.
Okay, sir.
Ma'am will hand over the session.
Yeah, ma'am. Kamakshi, ma'am.
Yes, ma'am.
Yes, ma'am. Am I audible, ma'am?
Yes, ma'am. Carry on.
Yes, ma'am.
Ma'am, I think resource person, sir has already joined, ma'am.
Join. Yes, ma'am.
Yes,
Just 1
yes,
minute,
ma'am.
ma'am. I will call to this.
Yes, ma'am. Yes, sir. Welcome, sir.
Yes, Sasikala madam.
Sir, good evening, sir.
Good evening, sir.
Sir, good evening, sir.
Good evening, sir.
Good evening, Yadavji.
Sir, thank you very much, sir, for accepting our invitation, sir. Thank you very much, sir.
Thank you, madam. It was a little hectic, actually, right? Okay, anyway, because you called.
Sir, even though you have a very busy schedule, but you accepted our invitation, sir. For that, always we are grateful to you, sir. Thank you, sir.
Yes, madam. Yeah, you want to have any 5 minutes break or you want to continue? I do not know exactly. Yeah.
Sir, before we start the session, first we welcome you, sir.
You
Sunita,
want me to
madam.
start?
Yeah, ma'am. Yes, sir. We shall continue the session, sir.
Yeah.
Yes, sir.
Already
Yes, sir. We will. Yes, participants, we welcome to the session on asymmetric cryptography challenges and solution. Welcome, sir. Our session expert, Professor C. Ramakrishna, sir. Sir, welcome, sir. Sir is Professor, Department of Computer Science and Engineering, from National Institute of Technical Teachers Training and Research, Chandigarh. Welcome, sir, to the session. Sir has been in various positions. Sir has served as Associate Dean, Product Development. Sir has been as a HOD, Department of Computer Science and Engineering. Sir is a senior member of IEEE USA and fellowship IETE. Sir has nearly guided 12 PhD scholars and 85 MTech people, MTech students, and sir participation in the academic years, nearly 30 years of teaching experience and research experience. Sir has been in the technical education for the past 30 years. Sir is the professor in charge for campus-wide internet administration, institute and web portal, NCTL, web portal and video lectures. Sir, areas of interest, I would like to pen few of it. Sir, area of interest, major domains are computer networks, wireless networks, cryptography and cyber security. Sir has been working in cloud computing, fog computing, and various domains of edge computing. Sir has nearly 130 research publications, both in national and international journals. And sir has been an active participant in various conferences and a member and advisory in various technical committees. So here goes a various list. Sir has been as a reviewer. Sir, few of it I will just mention it, sir. The list is very huge, sir. So here, sir has been as a reviewer for journals
and conference which are part of Elsevier, IEEE, Springer, Hindawi, and ACM. And sir has been a major contributor in undergoing a accreditation for Master of Computer Science, getting accreditation for a 6-year accreditation for the first time. And he has been a committee member AICTE to bring out examination reforms in technical education. Sir, we are very grateful, sir, to have you here. Sir, welcome, sir, to the session. I hand over the session to you, sir. Thank you.
Thank you, Professor Sunita Indra and Professor Sashikala. Can you hear me?
Yes,
Yeah,
sir.
sir.
Yes, sir.
Okay, that's great. Good.
Thank you, sir.
Let me share my screen. Thank you so much for your good words. And it is 8 o'clock, right? It's exactly 8 o'clock. And I assure all the participants, right? I'll leave you by 9 o'clock. Don't worry. I will leave you by 9 o'clock. Dot 9 o'clock. I will not take your time. Let's say some of you maybe for a dinner time. Some of you may be busy somewhere else. I could see a good number of participants joined over here. And I'll make it very light session. The session will be very light. And I request all of you maybe to keep your pen and paper ready so that you can do some small exercises in between, right? Small, so that you don't go to sleep or you don't feel bored, right? So I don't want to only give lecture, but I want to see that you will participate and you will respond in the chat window for the questions that are asked without unmuting, right? Because if you unmute, then it will be a chaos because there are many people are participating in this. Okay, so with these words, yeah, I hope you can see the slides.
Yes, sir. Yes, sir.
Okay,
It is visible, sir.
Yeah, as the madam has introduced, actually I was supposed to take this session on the second day, if I remember correctly. But because I had got some urgent work, then I requested her, because that's the sequence. Because in the first day, Professor Bindu has taken the session something on cryptography. I thought that I'll continue along with that so that makes sense. But anyway, Professor Sashikala did not leave me. Sir, you can come, you can deliver it on the last but one day and last day also, no issues. But I'll try to connect it. And first thing is, I congratulate all the participants for taking interest in attending this course. Because I started teaching this subject of network security and cryptography since almost 2007 or 8. That time when I was also not knowing what is this subject, but being senior most faculty in the department. So the turn came to me only, right? Because I was teaching computer networks, advanced computer networks, because we don't have UG program here, we have only PG program. So I was taking advanced computer networks, so therefore network security and cryptography came to me. So I took it as a challenge, and then I started taking interest in this subject. And I am fortunate, right? Because maybe because of compulsion or whatever you call it, I took it. And today we can see that every country is going digital, right? India is a huge country, right? Similarly, some other Asian countries, they're also huge nations. And in the world, we have 820 crores of population. And India alone, we have around 150 crores. And every government is talking about digital nation, digital India, and so on and so forth, right? So I was just going through some articles, and it is saying that India has around 90 crore plus internet users. 90 crore plus internet users. Our population is around 150 crores. 90 crore plus internet users. So you can see the scale of what we call security that is required when you are transacting through internet, electronic media, and so on and so forth. So you are all very lucky people that at least somebody is teaching you, right? When I started in 2007, so I learned myself maybe through various resources and other things, and then I picked up certain things. And subject of cryptography, right? When you talk about cybersecurity, one is a preventive step. Other one is when an incident do happen, right? We take all precautions, right? When we travel on the road, we take all precautions. But sometimes because not of our mistake, with somebody else's mistake also, accidents do happen. Then once the accident happens, what to do, right? So the same things will happen in the cyberspace also. Whatever preventive mechanisms that you take, how much cautious you are, but still there are chances of falling prey to the hackers, right? Falling prey to the hackers. And we see a lot of news on the television, we see a lot of news on the internet, and we see a lot of news in the newspapers. Even people who are having a lot of knowledge in this computer science and engineering field, right? They also do become prey for this type of attacks, right? I still remember, right, the Prime Minister's cybersecurity advisor, earlier cybersecurity advisor.
Excuse me, sir.
Yeah.
Sir, slides cannot move, sir.
No, I have not. I am just giving introduction only. Don't worry, right? I have not come to the second slide.
Thank you, sir.
I'm just trying to impress upon them that they should study this subject and become experts, and then encourage their students also to become experts in this area. So I'm just trying to build up the background, right? So that they should get interested and then move forward. So earlier cybersecurity advisor to the Prime Minister, right? He was one of the stalwart from one of the famous old IIT, right? Ex-director. And his account was hacked, right? His account was hacked and it was in the news. And 20 lakh rupees around has been taken away from his account. And I am 100% sure that even a 1 rupee also might have not come back to his account again. Because it's very, very difficult to trace these hackers and very, very difficult to catch them because it may be operated from several countries. Some places may not be having even the Information Technology Act also, right? If these type of incidents do occur, what to do? So it's a challenging field and it is a requirement of today, right? Even when US President, previous US President Barack Obama, when he came to India, right, he told that there are 5 or 6 areas every country should focus on. One of the area he touched upon when he came to India, when he was the president of US, but was the cyber security. So whichever country leads in cyber security, right, they'll become the leaders in the world. So you are attending such type of important course, which is being organized by this SRIT with the help of AICTE, and you are very fortunate. And I am going to talk something about preventive maintenance, preventive security, right? So this cryptography is basically comes as a tool. Before you actually transmit anything onto the cyberspace, you try to encrypt it so that you produce a ciphertext which cannot be understood by the hackers or illegitimate users, unintended users, unless until they have the key with which it has been encrypted. So therefore, you have 2 different types of cryptography techniques. One is symmetric key, other one is asymmetric key. We'll try to see some part of symmetric key today, and asymmetric key we'll see tomorrow afternoon. We'll continue that. And then you will appreciate that these techniques that which I'm going to teach today, which is being used widely in practice, but they have been developed somewhere around 1970 to 1975 or 1976. That means almost 50 years before. Almost 50 years before, the researchers have developed these techniques. Where at that time we were not knowing what is internet, right? We know, maybe we're all small children 50 years before. If you think yourselves, you are all small children. But the world on the other side has developed these algorithms, thinking that these may be required in future. That is the reason people will say that some of the countries are 50 years, 60 years ahead of each of us, because they think like that, they produce like that, and then which we are using it today. So we'll focus on symmetric key, what are the challenges, and then slowly we'll see what are the solutions also. I like this quotation, right? And I'm sure that many of you also will agree with this quotation, which has been said by Benjamin Franklin long back. 3 people can keep a secret only if 2 of them are dead, right? This is the greatest problem. Keeping something as a secret is the greatest problem for the human beings, right? It happens with me, and I'm sure that it happens with many of you as well, right? If not all of you. So when we talk about cryptography, there are 2 terms which will be coming again and again, right? One is encryption and other one is decryption. Hope the slides are moving.
Yes, sir. Yes, sir.
Yes, sir.
Keep it very light. Okay? Don't worry. So whenever you feel hungry or sleepy, let me know. I'll leave it immediately. So encryption is a process, right, which is done usually by the sender. It is a conversion of plain text. Plain text means the text that like I am speaking now. This is a plain text which I am speaking in English. And you all know English, so you are able to understand it. So converting this plain text to ciphertext. The ciphertext is the one which will be understood only by the intended destinations, right? For example, I am speaking in English and we all know English, so we are part of the class. So therefore, whatever I am saying, you are able to understand. You are able to understand. So decryption is the ciphertext which has been received, right? That has to be converted back to the plain text. So decryption is exactly the reverse of encryption. So whatever changes or transformations that you have done on the plain text at the sender side, that has to be exactly reversed on the receiver side so that you will be able to get back to the plain text, right? So this is something like this, right? Hello, John is a plain text that I wanted to communicate with the destination. So there is a encryption process. We'll see that slowly, right? What is this encryption process? And then this type of some ciphertext, right? When you look at the ciphertext and the plain text, right, you can see that ciphertext doesn't make any sense unless until you decrypt it. So this is ciphertext is the one which is transmitted onto the network or internet, and then it is being received by the receiver, and receiver applies a decryption process, which is exactly the reverse of encryption process. If it is successful, then it will get back to the original plain text, which is meaningful and understandable. So when we talk about aspects of encryption and decryption, 2 things are very important. One is the algorithm, a series of steps, right? And the other one is the key. So these algorithms, right? You have many algorithms under symmetric key, right? You have data encryption standard 1. You have data encryption standard 3, right? Data encryption 2 is also there, but 2 is having a flaw, right? Or it suffers from attack that is called meet in the middle attack, right? DES2, data encryption standard 2, suffers from meet in the middle attack. Therefore, it is not implemented in practice. So data encryption standard 1 is implemented. Now, currently, we are using data encryption standard 3. Right? A DES3. We call it a DES1, that is an older version, and DES3 is the latest version because attacks are becoming sophisticated. Your computational power is more available, and sophisticated systems are available, sophisticated tools are available. So therefore, DES1 is not recommended for financial transactions, and they've shifted to data encryption standard 3. So you also have AES, Advanced Encryption Standard, which is being used in many places, even your Wi-Fi devices also. When you go to the security, right, wireless protected access 1.0, 2.0, they all use this Advanced Encryption Standard, AES, right, that you can search and later on. Then you will find that AES is used in your Wi-Fi security also. So these are all the algorithms, right? DES1, DES3, AES, you have RC5, reverse cipher 5, and there are many more, right? You have even international data encryption algorithm. So many are available. These algorithms are available in the textbooks also. They are available in the research papers also. They are available as request for comments drafts also, right? So they're all standardized. They're standardized. They are available. You can download them. You can read them. You can understand them. You can teach those students. There is no secret in these algorithms, right? Algorithms are public. Right? In general, they are public, unless until they're patented or they don't want to disclose it. Otherwise, they are all public in nature and they are available on the internet. So what is the strength of this encryption and decryption is the key. Key is the one which is very, very important, very, very important. So when you talk about the keys, so we are talking about a digital infrastructures. We talk about a binary key because computer always works in a binary language. It can understand only the binary language, ones and zeros, right? The key is a binary key. And so what should be the size of the key? Size of the key is very, very important. See, we all remember in the, like I have done my BTech in, completed in 1992 from JN to Anantapur, right? So we used to stay in the hostel. So we were all students. We don't have much money, right? And we don't have many precious things in our room also. So we used to keep a very small lock, right? Small lock. And key is also small. And this lock can be opened even without key also, right? You can use ladies' safety pin and you can open this, right? Many a times our friends used to do that, right? Whenever I go home or they go home and bring some eatables. So without their knowledge also, right? We use a safety pin and then open the room and then eat the things which they have brought from home. And then again lock the room and then go back. So that type of key and that type of lock is also available. That means that type of algorithm is also available. That type of key is also available. But we cannot survive with that in cyberspace. So we need a robust algorithm, right? We need a robust key. So what should be the size of the key is very important for the encryption and decryption to be maintained. Encryption and decryption to be maintained. So when you talk about a binary key, right, it will start with a 1-bit key. So 1-bit key has two combinations, 0 and 1, right? The key can be 0, the key can be 1. Just like your briefcases, right? You can purchase the VIP briefcase or any other company, right? They have the number lock, right? So usually they have 3 rings, right? 1 ring, it is very easy to guess, right? Because there are only 0 to 9 options. So therefore, to increase the combinations, right? So that it's difficult to guess what is the key. So they have at least 3 rings. Some locks have 4 rings also, right? So that you have all the rings are having, 1 ring is having 0 to 9, other ring is also having 0 to 9, and third ring is also having 0 to 9. So to crack that, you need to have a lot of multiple combinations and permutations you have to try. So, but here it's only a binary key. So it is 1 bit means 0 or 1. It's easy to guess, right? You try with 0. If it doesn't succeed, try it with 1. So you don't require a computer for this to hack it. So if it is 2-bit key, it's a binary key. So 2 to the power 2. So 4 combinations, 0, 0, 0, 1, 1, 1, 1, 0, right? So 4 combinations also, you can do it manually. There is no problem at all. Then no computer is required. So 1-bit key is not useful. It's just like your safety pin, right? Just I gave an example. 2-bit is also like your safety pin. 3-bit, 4-bit, 5-bit, right? 6 bits, 7 bits, 2 to the power of 8, right? 8-bit key. So 2 to the power of 8 is how much? 2 to the power of 8 is how much?
256.
Oh, great. Very good. So I thought that you are listening or not. So 256. So how to know that 256 is a big number, right? For carrying out manually, which key has been used by the sender. So I have to try with all the keys. If you are applying a brute force attack, simple attack, then you have to try with the first key, second key, like all zeros, right? Then 00001, then 00010. So like that up to 256, you have to try all ones. So which is a very big exercise if you want to try it out manually. But if I want to use a computer, right? Today's computer, all of us have computers, right? The computer is in your hands, right? Your mobile phone also is a computer now, right? So if you think about a simplest computer, right? Simplest computer, maybe i3, i5, i7, i10, right? Which is having a, let us say, a 1 gigahertz processor for calculation purpose. Otherwise, your processors are now 3.4 gigahertz. They have a boosting clock frequency also. There are so many things are available now. But we take an average human being, right? Maybe a 1 gigahertz processor for simplicity purpose. 1 gigahertz processor means we understand and we assume that it takes 1 nanoseconds, right? If I want to convert into time, giga means 10 to the power of 9 gigahertz, 10 to the power of 9 gigahertz, 10 to the power 9 hertz. So if I convert that into time, frequency to time, then it becomes 1 by 10 to the power of 9 seconds. That is 1 nanosecond. So I assume that one permutation of the key or one combination of the key, right, to process it, it will take 1 nanosecond. So I have a 8-bit key. I have 256 possible combinations. How much time does it take to complete this exercise to know the key by brute force attack? Brute force attack means I'll start with all zeros, then 0001, then 0010, right? 11, 100, 101, like that. I go on one by one, right? So I complete all the 256, then only I'll be able to know what is the key. So one key combination takes 1 nanoseconds. So 256 possible combinations will take 256 nanoseconds. That is a brute force simple attack. But if I use a intelligent attack, then it may be half of this time only. But I am not an intelligent hacker. I am a simple hacker. I don't know much. So it will take 256 nanoseconds. 256 nanoseconds is much less than even 1 second. Right? The time space that the human eye can detect is only seconds, right? Below seconds, we can't detect it as human beings. So you have seconds, you have minutes, you have hours, right? So we can't understand with a simple eye what is milliseconds, microseconds, and nanoseconds. So 256 nanoseconds is 256 10 to the power of minus 9 seconds. So 8-bit key is not useful, right? It can be hacked in much less than 1 second. That means before you flip your eye, right, the key is in front of you on the screen. What is the key that has been used by the sender? Algorithm is already known. I told the algorithms are public, right? Algorithms are public. Our algorithm information is exchanged when you establish the connection between the source and destination. What type of security algorithm you are going to use? Key is the one which is going to give the strength for your security, and it is a 8-bit key which can be hacked within much less than 1 second. So 8-bit key is not useful, though 256 combination appears to be very big, but for a computer, right, it doesn't take no time to reveal the key. So let us make it double of it, right? Instead of 8-bit, let us go for 16-bit key. So if I use a 16-bit key, what are the possible combinations of 16-bit key? Total possible combinations: 2 to the power of 16. You all have read microprocessors, right? 8-bit microprocessor, 16-bit microprocessor. You might have done memory calculations. 2 to the power of 16 is how much?
65,536.
Oh, great. Very good. Thank you so much, right? Thank you. So 65,536 possible combinations. So same computer, we will use it again, right? 1 gigahertz processor, 1 nanosecond, 1 key combination. So 65,536 will take 65,536 nanoseconds. So 65,536 into 10 to the power of minus 9 seconds. That means 65,536 divided by 10 to the power of 9 seconds. So this is also a very small fraction of 1 second. So even 16-bit key also can be hacked in real time, right? Because it's much less than even 1 second. For the human eye, right? For the human point of view, it is looking like a very big key. But from the computational point of view, right, this can be broken in much less than 1 second. So therefore, 16-bit key is also not useful. So let us write 32-bit key. So 8-bit is not useful. 16-bit is not useful, right? Because it can be hacked at any time. And 32-bit key, what is 2 to the power 32? You have a 32-bit IP address, right? IP version 4. 32-bit, 2 to the power of 32. That's the reason I told you, right? Keep your calculator on your mobile phone ready. Keep your pen and paper ready.
Sir, 4.2949673 epsilon 9, sir. E power 9.
Okay. In terms of crores is how much approximately? In terms of crores, how much is it approximately?
429 crores.
Oh, great. Good. Very good. You are a good mathematician. Thank you so much. Thank you. Thank you very much. So it's roughly 430 crores, right? Approximately 430 crores. So 430 into 10 to the power of 7. 1 crore is 1 followed by 7 zeros, right? So 430 into 10 to the power of 7. So that is the key space, right? There are so many possible combinations of a 32-bit key. 430 into 10 to the power of 7. And our processor is 1 nanosecond, right? One combination of the key to be processed, it will take 1 nanosecond. So 430 into 10 to the power of 7 into 10 to the power of minus 9 seconds. How much it is? 430 into 10 to the power of 7 into 10 to the power of minus 9 seconds. How much it is? 430 into 10 to the power of 7 into 10 to the power of minus 9 seconds. How much it is? How many seconds? How many seconds? Okay, some people are putting some answers here. Okay. Hope you're all with me only, right? Not feeling hungry. Another 30 minutes only. Don't worry, right? I'm going to leave in 30 minutes. 430 into 10 to the power of 7 in 10 to the power of minus 9 seconds. How much? How many seconds it is? Okay. 4.3 seconds, right? 10 to the power of minus 9 into 10 to the power of 7. So 430 into 10 to the power of minus.
Yes.
How much it is?
4.3 seconds.
4.3. Thank you so much. Thank you.
4.3 seconds.
Yeah, Srinivasal Reddy, thank you so much. You saved me, right? I took engineering because I was weak in mathematics. So I thought that I am the only one weakest in the mathematics, but I found that all of you are also like me only. That is the problem. Anyway, so thanks to Professor Srinivasal Reddy. 4.3 seconds. 4.3 seconds is also, right, broken in real time. Because when we receive a OTP is valid for 1 minute to 20 minutes, depending on the level of transaction you are doing, right? 1 minute to 20 minutes. And whereas a 32-bit key that I've used for encryption, along with some robust algorithm, right? And my computer has given the answer of the key, which has been used for encryption in 4.3 seconds, which is less than 1 minute. Less than 1 minute. That means 32-bit key is also not sufficient. 32-bit key is also not sufficient. So researchers have used a 64-bit key, right? 64-bit key, 2 to the power of 64. Your mobile calculator will not help. You have to go for a scientific calculator only. Normal mobile calculator will not give you answer for 2 to the power of 64. You have to use scientific calculator. You can try it out later on your own. 2 to the power of 64 is a huge number, right? Huge number. And multiply that with 10 to the power of minus 9 seconds. You will get a huge number in terms of seconds. Then convert that into minutes. Good, Dr. Nirmala, thank you so much, right? You continue, right? Whatever I'm saying. So convert that into minutes, right? 1 minute is having how many seconds? Convert that. And similarly, 1 hour is having how many minutes? Convert that into hours. And 1 day is having 24 hours. Convert that into number of days, right? That also still the number will be big. Then convert that into number of years, because, right, 1 year will be having 365 days. So you will find the answer at the end roughly around 600 years. If you want to break a 64-bit key with the help of this 1 gigahertz processor, it will take 600 years, approximately 600 years, 590 to 600 years, right? You will get exactly around 590 or somewhere around that, 589. But for easy purpose, I'm telling you 600 years it will take. What is the average lifetime of a hacker? Right? When you start hacking at the age of, let us say, 10 years, you are a very genius person, right? At the age of 10 years only you have started. So you will live for actively for till the age of 60, 65, 70, 75 years. After that, you become old, right? And your computer, what is the age of your computer, right? In a government, central government department, ministry has issued a circular. Those PCs which are more than 7 years old, that should be absolute and they should be written off. They should not be used from the security point of view, right? Even your OS, many patches won't come because operating system has changed. So 64-bit key is impossible to hack. Impossible to hack because it will take 600 years for a simple desktop PC with 1 processor. Then you have supercomputers also, right? So it has been found that supercomputers also will take a good amount of time. Definitely not in real time, they'll be able to hack it. So that is the reason when we study, those who have studied data encryption standard 1, or if you have not studied it, right, you have a look at it. They have used a 64-bit key in the 1971. When this algorithm was designed in 1971-72, a 64-bit key has been used. When none of us knew what is a computer, what is internet, how to use internet, nobody was knowing it. But scientists have found out 64-bit key is really robust, right? And that means they have understood that next 50 years, what type of technology is going to come, how this computational power is going to be increased, but still they understood the importance of the key and they have chosen a safest key, right? 64-bit key. And later on, you will find that there is a key transformation process in DES1, right? So 64-bit key is transformed into 56, 56 is transformed into 48, and then such type of 14 keys are generated and 14 rounds it will perform. And finally, you will get the ciphertext, right? It is a very complex algorithm, right? But originally the key size is 64 bits. So to start with, 64-bit key is the safest key. So that's what I wanted to tell, right? So let us come back to this. So when we talk about encryption and decryption, algorithm is very important and which is in public domain in general. And key is the actually important one, right? The size of the key always gives security, strength and security to the algorithm that you're going to use, which is going to produce a ciphertext. So based on this key only, right? Based on this key only, there are two types of cryptography techniques. One is symmetric key cryptography, other one is the asymmetric key. What is symmetric key? You can understand from this diagram. This diagram I have taken from Cryptography and Network Security by ATAL Kahate book. That's a very simple book to follow, right? Those who are studying this subject for the first time. Cryptography and Network Security by ATAL Kahate. He is working in industry. He has written it in a simple manner, right? Because he is a implementer, basically, right? Implementer of this algorithm. So he wrote it in a very simple way. Those who wants to go with mathematics, then you can go for William Stelling's book or any other book, which involves a lot of mathematics also. But for beginners, I suggest Atul Kahate is a good book to understand. And then later on, you can build up your mathematical base also based on that. So if you look at the symmetric key diagram in a simple way, there is a sender A, there is a receiver B. Sender wants to send this plain text, right? So there is a encryption algorithm, right? You can see this lock and key. Encrypt with symmetric key K, and then it produces a ciphertext. That means I apply a symmetric key algorithm along with the symmetric key K on the plain text and then transform that into ciphertext and then transmit to the cyberspace. And then it is received by the receiver in the form of ciphertext. And the receiver is applying the decryption algorithm, which is the reverse of this encryption algorithm with the symmetric key K, right? That means the key that has been used by the sender, the same key has to be used by the receiver also for decrypting it so that it will produce the plain text back to the receiver side. So what is the problem here? Problem here is I wanted to solve that my plain text should go safely to the receiver side. So therefore, I opted the symmetric cryptography with the help of symmetric key K. But the demand on the receiver side is the same key has to be used. Whatever the sender has used, same key has to be used. So you solve the problem of plain text, how to send it safely. But you created another small problem, how to send this key, right? So key exchange, right? We'll see that in the coming slide. Key exchange is one of the biggest problem in the symmetric key cryptography. How to send this key, symmetric key K, safely to the receiver side. So one problem you solved it, but you created another problem, how to send this small key, a fixed size key, safely to the receiver side. So which is called in the research literature, key exchange problem or key distribution problem. So same key is used for encryption and decryption, which is good because you require only one key on the sender side and receiver side. Same key is required. There are a number of algorithms I told you, right? Symmetric cryptography, which are used in practice, but they have been developed many, many years before, right? I've already told you about DES. I told about international data encryption algorithm. I told about reverse cipher 5. There's a blowfish also. There is a AES, right? Which is being used widely in your Wi-Fi. It is used in SSL also, right? And these symmetric key algorithms are very popular and they are very fast. They're very fast. Because they are very fast, so therefore they are very popular also. They are very computationally not intensive algorithm because they don't use expensive mathematical operations, logical operations when they convert from plain text to ciphertext and ciphertext to plain text. So therefore, these algorithms are very fast, and that is one of the requirement of cryptography techniques. All the algorithms that you use for encryption, decryption, they should be fast, and that characteristic all these algorithms, symmetric algorithms have. So therefore, very popular, but they have a problem of key exchange. That's what we saw, right? Symmetric key K, right? It has to be shared by the sender to the receiver. safely. That is a problem, right? Key exchange is a problem. We will see that, right, one by one, how these problems are solved. And the other challenge with the symmetric key cryptography is it requires too large number of keys required for n communicating parties, right? That means if you have n number of users, if they want to have a secure communication with the help of symmetric cryptography, right, they require n into n minus 1 divided by 2 number of keys. This is a very large number, right? We'll see with an example. Then you will understand the difficulty with this n into n minus 1 divided by 2. I told that India alone is having 90 crore plus internet users. If all of them want to have a secure communication with the help of symmetric cryptography, this number will be very huge, n into n minus 1 divided by 2. And all over the world, if you see, I told that 820 crore population is available in the world. Out of that, 500 crore plus users are on the internet, right? Now, as just in the previous lecture also, you were listening about IoT, right? Internet of Things. Now, every device also wants to be part of the internet, right? Right? Your small devices, your sensors, everything wants to become part of the internet, right? So any device which wants to become part of the internet, right, they should have a IP address, they should have a key if they want to have a secure communication. So it is going to be a big challenge, big challenge. We'll see first the second one, how big is this problem? Then we will see the key exchange problem also, maybe tomorrow's talk. So take your pen and paper, right? If you are comfortable on the computer, you can do it also if you have a laptop or any device that you are using it. So this will try to solve it quickly, so that we'll be able to understand the second problem, right? Second challenge rather, right? Second challenge, how big it is. So we are taking an example, right? There are 300 crore internet users who wants to have a secure communication using symmetric key cryptography. So your job is to determine the storage space required to store the required number of keys, where each key is 64 bits in size. 64 bits, why I have used? Because I told you that to hack this 64-bit key with the help of 1 gigahertz processor, which is taking one permutation of the key or one combination of 1 nanosecond, it will take 600 years. So 64-bit key is safer, right? But we wanted to see what is the amount of storage space required if you want to have a secure communication among these 300 crore internet users using this symmetric cryptography. And you have to put your answer in terms of 1 terabyte hard disk, because that 1 terabyte is very common these days, right? Right? Okay. So we wanted to do that exercise. So your first job is you have to determine the total number of keys required. How do you get that? You'll get from this formula, right? Take your pen and paper, right? Or maybe computer. So n is your 300 crore. Okay. So n into n minus 1 divided by 2. So your job is, I'll be telling quickly, you can start doing it and you can start telling me what is your answer so that we can move quickly. So n into n minus 1 divided by 2. So n is 300 crores, 300 into 10 to the power of 7. So 1 crore is 10 to the power of 7, right? So 300 in 10 to the power of 7. Bracket n minus 1. So 300 in 10 to the power of 7 minus 1. So whether you remove minus 1, whether you neglect minus 1, it doesn't make any difference. So when you approximate it, it is on the numerator side, 300 in 10 to the power of 7 into 300 in 10 to the power of 7. So minus 1, I am just ignoring it. Minus 1, just I am ignoring it. You can approximate like that. And then divide it by 2. So 300 in 10 to the power of 7 into 300 in 10 to the power of 7 divided by 2. How much it is? Quickly, total number of keys for 300 crore internet users, symmetric keys.
4.5 crores around, sir.
Why 4.5? There are two 10 to the power of 7, right? 300 in 10 to the power of 7 into 300 in 10 to the power of 7 divided by 2. 4.5 is fine.
n into n minus 1 by 2, sir.
Okay. N into n minus 1 by 2.
300 crores into 300 crores minus 1 by 2. Around 4.5.
Expand that. 300 in 10 to the power of 7. So don't write it as crores. Expand that. 300 in 10 to the power of 7. Bracket 300 in 10 to the power of 7 minus 1. So minus 1, whether you do it or you ignore it, it doesn't make any difference, right? That's what I told you. Expand that crore, 10 to the power of 7. Then only otherwise you'll be confused. There are few questions here. Krishna Samdani is asking that, yes, once the quantum computing comes into picture, right? There is a question here. Then using cloud computational capabilities, it will be possible to break the key in a reasonable time. And also, what will be the future of the key-based algorithm once quantum computing? Yes, quantum computing comes into play. Even the safest RSA algorithm also may be broken, right? Safest RSA algorithm also may be broken in the coming days. That is the reason, right? Now they are developing. Once the quantum computing comes into play, right, in a real scenario, the way that we are using today, yes, your RSA will be modified, right? You will not use your RSA. Because RSA is safe because you don't have computational capability. You don't have computational capability. That is the only reason, nothing else. Good question. Very good. Yeah, what is the answer? How many number of keys? Yes, Mastan Pasha, you want to say the answer or you are talking with somebody? So what is the big mathematics in this? Yeah, yes, Sunita ji.
No, sir. Mastan sir, is it he wants to ask something or what? I just want to know.
I was just thinking, right? Because many people will be calling. They're all sitting at home, right?
Yeah, sir. Sorry, sir.
So disturbance will be there. You can't help.
Yes, sir. Please continue, sir.
Yes. So it is 4.5 into 10 to the power of 18 approximately, right? 300 in 10 to the power of 7 multiplied by 300 in 10 to the power of 7 divided by 2 is 4.5 in 10 to the power of 18 total number of keys. Okay. And each key is of 64 bits. Our key size is also there. Na? You remember the question now? Let me come back to the question. See, first is you have to determine the total number of keys. That we have already determined, 4.5 in 10 to the power of 18. And each key is of 64 bits in size. These keys have to be stored somewhere, right? A third party has to maintain these keys, right? So there is a key distribution center, right? Key distribution center, which maintains all these keys, and then it coordinates with the sender and the receiver. Okay. So these keys have to be stored. 4.5 into 10 to the power of 18 into 64 bits, because each key is of 64 bits. So total number of bits you will get, right? Then you convert this into bytes. 4.5 into 10 to the power of 18 into 64 bits. How to convert that into bytes? Divided by 8, right? 8 bits is 1 byte divided by 8. Then you will get the answer in bytes. But we want the answer in terabytes, right? Terabytes. So 1 terabyte you can approximate it, right? 1024 to the power of 4. Or 1024 into 1024 into 1024 into 1024. Or you can take it as 1000 also, right? 10 to the power of 12 straight away, right? Approximation you can take it. So it is 4.5 into 10 to the power of 18 into 64 divided by 8 divided by 10 to the power of 12. So that the answer will come in terabytes. So my answer says, because of lack of time, right? I am not giving time to you. I require 3.6 crores of 1 terabyte hard disk to store these many number of keys. 4.5 into 10 to the power of 18, 64-bit size keys. I require 3.6 crores of 1 terabyte hard disk. That is 3.6 into 10 to the power of 7 number of 1 terabyte hard disk. What is the cost of 1 terabyte hard disk in Anantapur? What is the cost of 1 terabyte hard disk? Normal hard disk, not the SSD. Simple hard drive. What is the cost of 1 terabyte hard disk in your city?
Nearly 6 to 7K charge, sir.
Oh, 6 to 7,000, huh?
Yes, sir. For
Around
SSD, sir.
3,000-4,000.
Is selling at 2,500 approximately. Okay, so okay, that's good. So let us take it as all over India price is 5,000 approximately, average, right? Average, keeping the medium, small towns and then big cities and all things put together, 5,000 rupees, right? So total number of hard disks is 3.6 crores, and each hard disk is costing 5,000 rupees. So 3.6 crores multiplied by 5,000. It will be coming to around 18,000 crore rupees. That means if you want to implement the symmetric cryptography solution for the 300 crore internet users for secure communication, you need 18,000 crore rupees for only storage. Only store these keys, 64-bit size keys for all these 300 crore internet users. But you have to run a data center, right? So if you need servers, apart from the storage, you need servers, you need internet connection, you need AC, right? You need many other things you require. You need manpower, right? You can imagine, right? What is the size of this problem actually, size of this problem. So that means this number of keys required for n communicating but too large is a big challenge actually, big challenge because of the size of the internet. Size of the internet, I told you the worldwide is 500 crore plus internet users are existing as on today, and this size is increasing because it's not only human beings trying to use this internet, because it is being assigned to some sensors also, right? And you are talking about Internet of Things, you are talking about wireless sensor networks, you are talking about body area networks, right? There are many technologies are coming up for various purposes, and every device has to be secured. Every device which is part of the internet has to be secured. Otherwise, it's going to be very tough. So this is a big challenge, right? So to solve this problem, two people like you and me, right? They attempted this problem. So this is called a Diffie-Hellman key exchange problem. Okay. So one is the number of keys required. That is one problem. Other problem is the key exchange problem. So this number of keys problem we will see later on, right? Tomorrow. And key exchange is another problem. How to solve this key exchange problem? So Diffie-Hellman is two people. Diffie was the student of Professor Hellman, right? One student and one teacher. They have invented this algorithm long back, right? Around 1975 or 76 or so, when many of you are small children or you are not born in this world. Okay. So they have attempted the solution for the first problem, key exchange problem. That's why it's called Diffie-Hellman key exchange protocol, or it is also called as Diffie-Hellman key determination protocol. So don't be confused, right? As the name itself indicates, it will only give you the symmetric key, right? It will not do any encryption. It will not do any decryption. Only the key that is going to be used for encryption, the key that is going to be used for decryption, sender side and receiver, it has to be same. This algorithm gives only the key, symmetric key, without exchanging the key. So Alice and Bob can decide upon a key without meeting. Alice and Bob, because they are foreign names, because inventors are foreigners. You can also use Ram and Sham, no problem, right? To understanding purpose. No secrets are exchanged, and yet a secret key can be agreed upon. Right? Another 15 minutes will wind up, don't worry. So Diffie-Hellman key exchange, there are only 7 steps. You can see the right, 1 to 7 steps are there. In these 7 steps, symmetric key is decided by the sender, by the receiver, without exchanging the symmetric key. That is the beauty of this algorithm, right? First step is Alice and Bob agree on 2 large prime numbers, right? N and G. Let us call them N and G. What is the prime number? I think all of you know what is the prime number.
A number
divisible by itself.
Anjali Pandey.
Yes, sir.
What is a prime number?
So it is divisible by itself.
Half answer you have told me.
divisible by 1 and itself, sir.
But divisible by 1 in itself.
Good. Nice. Anjali Pandey is also right. She did not tell the other part. But a prime number is a number divisible by 1 and itself only. Right? 1 and itself only. Good. Very good. You are very good in mathematics. You are all. So we need large prime numbers. Large prime number. How large? As large as possible. So what is the largest prime number? Do you have any idea how many digits are there in that prime number? Any idea you have? You can give a Google search and find out, right?
So recently it was found. There was the largest prime number was calculated, I guess.
Yeah, it was on 12th October 2024. Yeah. The largest Mersenne prime is having 4 crores 10 lakhs 24,320 digits. It was found on October 12th, 2024, recently only, right? Just 2 months before, exactly 2 months before. So there is a team called Great Internet Mersenne Prime Search, GIMS, right? GIMPS. So their job is finding out these large prime numbers, right? Large prime numbers. So it is having 4 crore digits in that number, 4 crore, right? We are comfortable with our one digit prime number, 2 digit prime numbers, and 3 digits, right? Maximum 2 digits we can do manually. But after that, you need to have, right? You should be like a Shakuntala Devi, right? But none of us are Shakuntala Devis. That is a problem, right? So how large is the prime number? As large as possible, so that it is not easy for the hackers to guess this n and g. These two integers need not be kept secret. They are actually public, right? That means n and g, they are very large in size, prime numbers, but they are not kept secret. That means they are public, right? And they are traveling on a insecure channel between Alice and Bob. That means Alice will choose this n and g and sharing with the Bob, right? These are my n and g, and they are traveling on a insecure channel or not encrypted channel, right? That is, neither the numbers are encrypted, neither the communication channel is encrypted. That means they are traveling in a plain text between Alice and Bob, and they are not secret. Second step is the sender Alice chooses another large random integer number x and calculates a value. A is g to the power of x mod n. So g is second prime number. X is chosen in the second step by the sender only. And n is also another prime number, g to the power of x mod n. So modulus, right? You know the modulus, right? How to do it. And what is this random number? How to generate random numbers? How to generate random numbers? Any idea?
So normally we can use NIST provides us with some random number strings on
Hey, does your compilers have random number generators? You are using many compilers, right? You use C++ compiler, use your MATLAB, you use many other things. Do they have any?
They have inbuilt functions and all which we can use.
For example, like how do they look like in C++ or C?
Rand functions, I suppose. Good. If I want to.
Yeah, Krishna Samdani, thank you so much, right? You are familiar with it. So you can use rand function, right? There are varieties of rand functions are available. Vinola is also right. Library functions are available. Or you can also write your own function. How to generate the random numbers. If you don't want to use, you can use one of the best random number generators, Mercinnet Twister. Right? The random number generator that comes with C compiler, C++, they are weak. Right? If you want a very strong one, right, a robust one, you can use Mercinnet Twister and variations of it that you can find out on the internet, and you can use it for your purpose. Okay, anyway, good, that's good. So random number, integer number we want, large random integer number x, right? It should not be small, it should be large, so that it is not easy for the hacker to guess. So calculate the value of a. This is the second step. So after calculating the value of a, the sender Alice sends the number a to Bob, right? Again, it is you can see here, it is an insecure channel. That means neither the number is encrypted, neither the channel is encrypted end to end, right? So A is also actually public. N is public, G is public, A is public, because they are traveling in a plain text to the receiver side. Bob independently chooses another large random integer y and calculates the value of B. What is B? G to the power of y mod n. So N and G already given by Alice only, and y is chosen by Bob himself. Right? Y is chosen by Bob himself. So Bob sends this number B to Alice. So B is also traveling in the plain text to the sender side, right? A is also traveled to the Bob side in the plain text. N and G also exchange between Alice and Bob in the plain text. So N, G is public. Capital A is public. Capital B is public. And then in the sixth step, Alice now computes the secret key K1. That is a symmetric key K1. So what is symmetric key K1? B to the power of x mod n. Right? Alice is having the B. B from where it has come? Bob has sent this to Alice. So I have Bob's number, this private key, to the power of x. X is, who is having this x? X is with Alice only, right? You can see in the second step, x is generated by Alice only, right? B to the power of x mod n. N is the another prime number. So you can calculate K1, no issues. Similarly, Bob now computes the symmetric key K2. K2 is a to the power of y mod n. A value was received from the Alice. Y is chosen by Bob only. And n is, and the first step they have exchanged it, right? So a to the power of y mod n also you can calculate. Okay. So when I run this Diffie-Hellman key exchange protocol or key determination protocol, all these 7 steps, right, sequentially, what will be the value of K1 and K2, right? You have to tell me whether K1 is equal to K2, K1 is greater than K2, K1 is less than K2, or you do not know.
Both are same, sir. Both are same.
Okay, how do you say that?
K1 equal to K2, sir.
Okay, very good. So simple, right? Thank you so much. So how to do that? You substitute this B value, right? What is the B value? B value you can see here, right? You substitute this B value here. Okay. And you know modulus operation, how to do it. So it becomes G to the power of Y whole to the power of X mod n. Substitute the value of A. What is A? A is here, G to the power of X mod n. Substitute it here. Then you do the modulus operations. Then you will find that K1 is actually G to the power of Yx mod n, and K2 will be G to the power of XY mod n. So whether it is G to the power of Yx or G to the power of XY, mod is same, right? Mod n is same. So therefore K1 and K2 will be equal, right? So what is the requirement of symmetric key? Symmetric requirement is same key has to be used by the sender and by the receiver. This is the problem. Now, if you look at this algorithm, key is not exchanged, but key is determined, right? Alice has determined the key on its own with the help of these previous steps, and Bob has decided K2 following the previous steps. And the beauty of the algorithm is at the end of the algorithm, K1 is equal to K2. Now, what is the strength of this algorithm? Why it cannot be broken? Right? I told you that N is public, G is public, capital A is public, capital B is public. So why K1 and K2 cannot be calculated by the hackers?
Because of X and Y.
Okay. So X and Y, they are secret, right? You can see here, X and Y are secret. Alice has chosen this X value, Bob has chosen this X value. They have not shared these values, right? A is shared, B is shared, but X and Y are kept secret. So when you try to find out from this K1 and K2, what is the value of X and what is the value of Y, by rearranging this equation, it lands up in a discrete logarithmic problem. Discrete logarithmic problems are very, very hard to solve, right? There is no perfect solution in all the general cases for discrete logarithmic problem. So Diffie-Hellman has demonstrated to the whole world that their algorithm is safe and secure, which was invented in 1975. So whole world found that this 7-step algorithm, a beautiful algorithm, right, which has solved the first problem of symmetric key exchange problem, or key determination problem, or sharing the symmetric key problem is solved with the help of simple 7 steps. There is no complex mathematics is involved. Simple algorithm, right? Only some calculations you have to do, some numbers you have to choose, right? Prime number and random integer numbers you have to choose, and you have to do some modulus operations, and you will end up in the symmetric key, right? And if you try to find out what is the value of X and Y, you will end up in a discrete logarithmic problem which doesn't have a perfect solution. So therefore, the algorithm is safe. So can we do it one example quickly? Okay, can you solve this and tell me before we wind up? Write down these numbers. N is 11, G is 7. The algorithm says that prime numbers have to be very large, but I have taken very small because we wanted to just understand the algorithm. So once you implement it in practice, right, through program, then you can use large numbers. And X and Y, random integer numbers, they should be as large as possible, but still I have taken only 1-digit numbers for understanding purpose. So write down these numbers and put these numbers in these equations, right? First you calculate the value of A, calculate the value of B, calculate K1, calculate K2. But that's all. And let me know what is A, what is B, and then K1 and K2 in 5 minutes. Then we'll wind up. Fast, huh? I know that you're all good in mathematics. If you calculate the value of A, you can put it in the chat window. Whoever has calculated, you can put it in the chat window.
So I have a query, if I can ask.
We will answer your query. First put this solution here, then we will listen to your question also.
Sure.
Sir, can you provide the numbers again?
Okay, sure. N is 11, G is 7, X is 3, Y is 6. You want to see the algorithm also?
No, no, sir. No, sir.
Okay, I'll show you the algorithm also, right? Okay.
So is it 9?
You are telling about K1?
K1, K2.
Okay. What is the value of A and B?
A and B will become 2 and 4.
Okay, very good. So let us wait and see others also. Do they agree with you? Yeah. Anybody else? See, capital A is G to the power of X mod N. N is 11, G is 7, X is 3, right? So G to the power of X. G is 7. 7 to the power of 3. 7 to the power of 3 mod 11. How much is it? 7 to the power of 3 mod 11.
It will be 2.
Great, wonderful, wonderful, Anjali Pandey, right? Then similarly, B. B is G to the power of Y mod N. G is again 6, 7. Y is 6. 7 to the power of 6 mod 11.
4.
Okay, good, very good. When you feel hungry, answers will be automatically coming.
4, sir. 4.
Yeah, I know that. You are all very good. So, A is 2, B is 4, na? B is 4. Okay. Okay, good. So, what is K1?
9.
Okay, K1 is B to the power of X. What is B?
4 to the power 3 mod 11.
4 to the power of 3 mod 11. So, that is 9, huh?
Yes,
Yes, sir.
Okay. So, what is K2? K2
Also
is
9.
A to the power of Y. A is 2,
Yeah,
right?
it
2
is
to the
2
power
to
of
the power
6
6 mod 11.
mod 11. So, this is how much it is?
9.
Okay, good. So, you do not have to ask me whether your answer is right or wrong. So, if K1 and K2 are same, then your answer is correct. If K1 and K2 are different, then your answer is wrong.
Wrong.
Because Diffie-Hellman has shown that at the end of the calculations, mathematically also, that K1 and K2 will be same. It has to be same. If they are different, that means you have done something wrong somewhere. Okay. So, it's a beautiful algorithm, right? Beautiful algorithm. We'll see in the tomorrow that this algorithm suffers from, this is answer, right? A is 2, B is 4, K1, K2 are 9. Those who have got this answer, absolutely correct, right? Even those who have not done it, you can do it leisurely tomorrow morning and you will get it, right? And you can try this problem also, right? Write a program and try it out. Any language of your choice, right? Language is not a barrier. Any language you can use. Right? You can write down the question and you can solve it. We have taken only a 1-digit and 2-digit prime numbers, but here we are taking 10-digit prime numbers. So even this generating these prime numbers is also a research area. You know that, right? How to generate large prime numbers is itself a research area. Okay. So that is the reason there is a group, GIMPS group is there. So their job is researching on these prime numbers only. Right? There are two popular algorithms are there, which you may be aware that determining the primality test. Right? There is something called a Miller-Robin test. There is something called a, I'll just give you the names, you can find out, those who are interested. Miller-Robin test. This is a world famous primality test. World famous, like there many are there. One is there from India also, right? That is called AKS. AKS primality test, which is called Agarwal, Kayal, Saxena. They are from IIT Kanpur, right? They have also invented one algorithm that is also quite popular. So Miller-Robin test is a older one and AKS is a newer one. Miller-Robin is a probability-based test and AKS is a deterministic-based. But Miller-Robin is more popular, and like that, there are many more primality test algorithms are available. So India also has contributed to this primality test, right? AKS algorithm, Agarwal, Kayal, Saxena algorithm, which is also used for determining the primality of a given positive integer number. So you can try this also. But unfortunately, right, just like the previous speaker also was telling you at the end, right? So what are the issues? You have a denial of service, denial of information, then man-in-the-middle attack. So this Diffie-Hellman key exchange protocol, which we have studied, right? This we will study tomorrow, right? Diffie-Hellman key exchange protocol is very wonderful, right? 7 steps are there. You've got the key. and they have demonstrated that you can't determine X and Y. If you try to determine X and Y, it will lead to discrete logarithmic problem, which doesn't have a solution. Therefore, Diffie-Hellman key exchange protocol is safe and secure, which can be used in the internet. But the hackers are more smarter than Diffie and Hellman, right? They are more smarter. Because hackers also knew by following this Diffie-Hellman key exchange protocol, trying to determine X and Y is impossible. Because Diffie-Hellman, they themselves have demonstrated it's impossible. So hackers never tried this method which Diffie-Hellman has suggested. They followed a simple trick, right? That's called a man-in-the-middle attack that we'll try to understand tomorrow, right? With that simple man-in-the-middle attack, this algorithm is broken. This algorithm is broken, and key has been determined by the hackers also, just by playing the trick of man-in-the-middle attack. Man-in-the-middle attack. Okay, so that we will see tomorrow how this man-in-the-middle attack occurs, and then how the communication between the sender and receiver will be hijacked without their knowledge, right? They don't know there is something called a man-in-the-middle attack, and then they are not aware of it, and their communication has been hijacked by the hacker. Right? That we'll try to understand with this example tomorrow, right? Now it is 9:05. I promised that I'll leave you at 9 o'clock. So I have taken 5 minutes more. Thanks to the previous speaker, right? He has taken good amount of time, and I'm very happy about it because I have got lesser time, right, to interact with you, and it's 9 o'clock. Yeah, yes. So I am done for today, and tomorrow I think 2 o'clock or 2:30, Shashikala madam.
2 o'clock, sir.
2 o'clock, 2 to 3:30.
Yes,
okay,
sir.
okay,
Yes,
right,
sir.
right. I'll be available. Yeah. Any questions so far up to here?
Yes, sir. Sir, I had one question.
Yeah.
We were talking about the key size. So nowadays, when we are talking about IoT applications, where they are not able to have a computational power is not so high. So
Yes.
when we want key size to be less for those kind of applications, then how are
Yes.
we going to keep a trade-off between the security part and
Yeah,
the
yeah. There are the very nice question Krishna Samdani has asked for it, right? For lightweight devices, this whatever cryptography technique that we are studying for these normal devices, which we have this desktop computer, laptop, right, where there is a lot of computational power is available. But it is a nice question that there are a lot of IoT devices are coming, sensor devices are coming. Everything needs security. So there is a separate subject going on along with this normal cryptography. There is something called lightweight cryptography. So you must read that lightweight cryptography techniques. Many techniques have been developed to, right,
Yes,
which can ensure security for those devices also with a smaller key size also, right?
Okay.
So you can read lightweight cryptography. There are n number of algorithms are available. That is also another research area which you can explore.
Correct.
Okay.
Okay. Thank you.
Yeah. Good. Very wonderful participants, right? At 9 o'clock also you are excited to understand, you are excited to listen. And then at the end, Shashikala madam is also circulating attendance, I believe.
Yes, sir. Yes, sir.
Yeah. Okay.
Sir, thank you very
If
much.
you don't have
sir.
any other questions, we'll meet at 2 o'clock tomorrow. Right? Thank you so much. You are all wonderful audience. Thank you so much.
Thank you
sir.
very
Thank
much,
you
sir.
so much.
Thank you.
Thank you, sir. Thank you.
Participants, we have some small announcement regarding tomorrow's schedule. So tomorrow is the last day of our faculty development program. So before that, I would like to convey some important instructions regarding tomorrow's schedule. So tomorrow we have 3 sessions. We start at 2 o'clock. From 2 to 3:30, we have one session that is handled by Professor Ramakrishna sir, NITTTR. Again, session 2 starts at 3:30 to 5. So this session will be handled by Jainab madam from Muscat. And the third session we have from 5 to 6:30 p.m. That will be handled by Sairam sir. So sir is already handled one session in the second day. So the same resource person will handle this session. And after that, we have validatory followed by feedback from participants from 6:30 to 7:30 p.m. At around 7:30, we have the test link. So here at the end, we must be careful to get the certificate. So to get that certificate, it is mandatory to give the feedback in the ATAL portal. No, make a note of it. Everyone should login into your ATAL portal account, and you have to provide the feedback. it must be, it is mandatory to get the certificate. And the second important instruction is you must write the test. After that only you need to get the certificate. So these are the two things you have to complete from your end. From my end, we complete the attendance. We need to post the attendance in the ATAL portal. So these are the three things we have to fulfill to get the certificate. So that's why I request every participant to take the test as well as to give the feedback in the ATAL portal. Regarding attendance, I will take care. Okay, thank you very much. If you have any doubts, you can ask me.
Ma'am?
Ma'am, tell me, ma'am.
Yeah, actually, I need a question. I need to ask one thing that tomorrow we need to log in into our ATAL portal and then only we can give the feedback form. That will be generated automatically there?
Yes, ma'am. Feedback will be enabled tomorrow for everyone, ma'am, in the ATAL portal.
Okay. And what about the test? That will be at the same timing only, that is 7:30?
Test link we will post in the group, ma'am. You post in the group or in the chat box, ma'am, during the at the end of the session.
Okay.
Yes, ma'am.
Okay. Thank you, ma'am.
Okay.
Ma'am, can you guide us to fill the feedback in the ATAL portal?
Sir, we will give the instructions in the morning, sir. We post in the WhatsApp group, sir. What are the steps you have to follow? How you give the feedback in the ATAL portal, sir?
Have you posted, madam, in today's
No,
morning?
not yet, sir. Tomorrow
Tomorrow.
morning we will post in the group, sir.
Okay, ma'am. Thank you, ma'am.
Okay, sir. Okay, Hemant sir, shall we wind up the session, sir?
Yes, madam.